The following message is best viewed on an oscilloscope.
Hello, can you hear me well?
Yes.
Okay, thank you very much. So I'm Yasu Okumura from University of Tokyo, and I'm one of the organizer team for the Higgs track, and I'm chairing this session with Valerio for this morning. Yeah, welcome to the Higgs session today, and yeah, let's start the Higgs track. And today we will have the Higgs physics at the future lepton colliders and the search for the Higgs pair production mode at LHC will be presented. And also later we will have the updates on the higher order diagram contributions in the Higgs sector will be also shown in this session. So then let's start the discussion. Yeah, the talk will have the 18 minutes and we have the 15 minutes allocated for the talk. And the last 3 minutes is for the question and comment. And I will pass the information for the remaining 2 minutes during the talk. So then, yeah, please adjust your speed for the discussions. Okay, then let's start the main part of the discussion. Excuse me, I need to start the record. Excuse me. All right. So yeah, then let's start the discussion. The first speaker is Mikael, and yeah, he will discuss about the expectations for the precise tests of the standard model at the ILC. So yeah, thanks a lot for sharing your camera, and please go ahead.
There we go. Okay. It's a beautiful afternoon in Tokyo. It's the middle of the night here. It's a crazy world. But let me tell you about the precision tests of the standard model at the ILC. I'm representing the LCC Physics Working Group. Actually, there are a large number of talks on ILC physics at ICHEP 2020. Here's a list of them for your future reference. Most of them are going on in parallel right now, but what can I do about that? If you have any questions about these talks, we're opening a discussion room this afternoon, European time at 4 p.m. So please, for extended discussion or questions, join us there. I think all of the speakers will be there in this room. Okay. There's now a well-established physics case for the construction of an E plus E minus Higgs factory, an accelerator which is designed to study the properties of the Higgs boson with high precision. So in this talk, I'm going to review the expectations for one of those projects, the International Linear Collider, to test the properties of the Higgs boson and to carry out other precision tests. The ILC has recently gotten an impetus from the European Strategy for Particle Physics. One of their conclusions is an electron-positron Higgs factory is the highest priority next collider. And also, they pointed out that the timely realization of a Higgs factory in Japan would be compatible with that strategy and attractive to the European particle physics community. So I think it's time for everyone to learn about this stuff. And so let me go ahead and talk about that. By the way, here is the, we hope, the schedule for the International Linear Collider. Actually, this weekend or early next week, the ILC will enter its next phase with the establishment of the International Development Team hosted by KEK. Please look at the announcement before the end of ICHEP. And then our current understanding of the next stages is in 2 years, the establishment of the ILC pre-lab at KEK. Within 3 years after that, the establishment of the ILC laboratory and the start of construction. And we're looking forward to the first data in the mid-2030s. Well, the first goal of the ILC is to produce 500,000 Higgs bosons in the reaction E plus E minus to ZH. These are not your ordinary Higgs bosons as you might find at the LHC. These are tagged Higgs bosons, tagged by a Z at 110 GeV laboratory energy in an environment with very little background. By counting, you can establish the Higgs boson branching ratios and search for invisible and exotic Higgs decays. At the same time, we can study the other prominent reactions in E plus E minus, W pair production, fermion production, and Z gamma. Z gamma has, as a part of it, the return to the Z with radiation. So that also allows us to do precision electroweak. And we'll talk about all of these reactions in the course of this talk. Further reactions become available as the ILC is raised to higher energies. In fact, we want to measure all of these reactions because they work together in a very powerful way. Let's make the assumption, which seems very reasonable in light of LHC results, that new physics beyond the standard model is generated by heavy particles up there somewhere with minimum mass m. To describe processes at the scale of the Higgs mass, we integrate out these particles. The resulting effective Lagrangian is of the form that I've written on this slide. L4 is the most general set of interactions with the standard model gauge symmetries and the standard model content. And as you all know, that's exactly the standard model. So the corrections to the standard model come in terms associated with higher dimension operators with the gauge symmetries of the standard model. The OIs at dimension 6, the OJs at dimension 8, etc. If we make the approximation that only the dimension 6 terms are important, and that's very reasonable in the sense that currently the corrections to the standard model are quite small, then this is a finite problem to work out the coefficients of the CIs. Many measurements can then fill in the full picture. This is the current situation on the couplings of the Higgs boson, maybe not current as of this meeting, but current as of the most recent compilation I could find from Atlas in 2019. It's quite striking that the coupling of the Higgs to many species are observed and agree with the standard model to an accuracy of somewhere between 10 and 30%. It looks very impressive until you start thinking about it just a little. In terms of the SMEF, though, this is not an impressive verification of the standard model. Deviations in the Higgs boson couplings, according to the formula that I wrote on the slide before last, are expected to be of order mh squared over m squared, that is for heavy m at the few percent level. Confident discovery of these signals requires sub 1% measurements. And this is the aim of a Higgs factory, to provide measurements at that level. In the next talk by Daniel Jeans, you'll hear more about how the measurements are actually done. Here I'm going to discuss their interpretation. On the other hand, the Higgs boson has many decay modes, and all of these decay modes are accessible to experimental measurement in the clean environment of a Higgs factory, including, for example, charm, the direct measurement of the Higgs to glue width, etc. Interestingly, different modes of Higgs boson decay different models of new physics affect the Higgs boson couplings in different ways. Very roughly, an anomaly in the couplings to B and tau signals supersymmetry or a 2 Higgs doublet. Anomalies in the coupling to W and Z signals composite Higgs or the presence of a Higgs singlet. Anomalies in the couplings to gamma, G, and top signals top partners or maybe top condensation as a part of the symmetry breaking mechanism of the standard model. It's interesting then, the search for new physics in the Higgs couplings is a new approach to studying physics beyond the standard model. It's orthogonal to the conventional approach of looking for new particles at the LHC, and it has a lot of information in the sense that the Higgs has many couplings which are affected by different types of new physics in different ways. Here's an example. This is from a paper by Wells and Zhang. The colored bands represent, as you see on the right, the deviation of the Higgs coupling to BB bar, with the somewhat yellowish band being a 5 to 10% deviation. The solid line shows the region currently excluded by LHC searches in the class of models they describe, and that will be extended at HL-LHC. But beyond that, there's a whole phase space which will be unexplored by the LHC, but which can be reached by this orthogonal technique. And in that way, we hope to really get beyond the standard model. Here's an illustration of a bunch of different models, and it gives the impression, I think the very correct one, that different kinds of models affect the Higgs couplings in different ways. Now, in general, the standard model effective field theory has a large number of possible operators and possible degrees of freedom. There are 59 baryon and lepton number conserving dimension 6 operators for one generation and about 2,500 for 3 generations. So it's a challenge to fix all of these coefficients uniquely. And very often in talks from the LHC, you'll see constraints on these parameters one at a time, for example, or in small groups. However, E plus E minus reactions give a special situation. Actually, if you omit fermions and concentrate only on gamma, Z, W, and H, there are only 7 CP conserving operators. And when you add fermions at an E plus E minus collider, typically you're only adding the electron. And so the number of operators is also very few. Actually, the Higgs boson couplings are determined by a system of only 17 CP conserving operators. And actually, E plus E minus to W pairs and precision electroweak involve the same set of operators. So if we measure all of these reactions, we can put them together into a single fit and get very powerful constraints. Here's for your amusement the list of operators. Let's not spend time on this since time is advancing. Let me just note that precision electroweak is actually a nice property that can be studied at the ILC, both by radiative return, as I've already pointed out, or by a dedicated so-called giga-Z run at 91 GeV. Giga-Z here is 5 times 10 to the 9 Z's in the program that we've defined. In either case, you have the advantage of polarized electron and positron beams, and these really provide some big advantages. They allow the measurement of polarized observables, which are in general much more sensitive to sine squared theta W and other important underlying parameters. And with electron and positron polarization, you have crucial checks on systematic errors in a game where systematic errors are very important given the level of precision. In the talk by Jenny List yesterday, you can go back and look for it, there's an interesting discussion of how we're going to get a very precise handle on these polarization observables. Here's a table of the projected errors, Z-pole in the middle and radiative return on the right, compared to the current values. This is not tera-Z, as you would have at a circular E plus E minus collider. But actually, if you compare this to the FCC projections, it really stands up pretty well. We're going to improve all of the precision electroweak observables, maybe just not the Z mass, by more than an order of magnitude. Some of these observables get very close to the tera-Z values. In particular, the value of sine squared theta W is very close. And here we really believe that we have control of the systematic errors due to the use of polarization. So this is already a quite impressive program. E plus E minus to fermion-fermion is also a very interesting program in addition to the Higgs. Each reaction is modified by 4 dimension 6 contact interactions. But actually there are 4 observables. If you measure the cross-section and the forward-backward asymmetry, or another way, the forward and backward cross-section, from each of two initial states of beam polarization, you can measure those four coefficients independently. And this allows searches, which are actually very sensitive. Here's a little table of them from the reference given at the bottom. You notice that by the time the ILC gets to 500 GeV, we're well into the range of compositeness scales, which are above 100 TeV. And so really probing to a very great extent the presence of these possible contact interactions. And actually, again, independently for each species and polarization. Okay, now back to the Higgs couplings. Putting all of this machinery together, we can extract the absolute Higgs boson couplings using a fit to standard model effective field theory. The fit that I'm going to show you has 22 parameters, namely 16 coefficients. The one that's missing is the triple Higgs coupling, which we'll come to at higher energy. 4 standard model parameters, and just to really include everything, we include 2 parameters for invisible on the one hand and unclassified on the other hand, exotic decays of the Higgs boson. Into the pot go precision electroweak measurements, precision measurements of W pair production, of course, the battery of Higgs measurements, and also some particular HLLHC inputs. For example, the ratio of the gamma-gamma to 4 lepton partial widths of the Higgs. Please see the papers at the bottom for a description of how this works. Here are the projected results.
2 minutes.
Absolutely. You see the level of 1%. This is the Higgs coupling precision in percent. You see where 1% is across the middle of the slide. And you see that already at 250 GeV, we expect to be there for the most important Higgs couplings to Z, W, B, and tau. As we increase the energy and add Higgs data from W fusion, these events, this precision gets a lot stronger. Red takes you all the way to the projected ILC at 1 TeV. And you see there, if you look at the left, we're talking about a 2% measurement of the Higgs to TT bar coupling and a 10% measurement of the Higgs self-coupling. So really the ILC has the power to survey the full complement of Higgs decays, the entire profile of the Higgs boson. This slide shows the comparison to HLLHC. Now HLLHC extractions of the Higgs couplings are all model dependent. So to plot ILC here, we've made the same model dependent assumptions. Everything gets a little better, but really these are the numbers that count if you want to prove that you have new physics beyond the standard model. Let me just say that comparing to other Higgs factory proposals, it turns out they all have essentially the same projected performance. So it doesn't matter which one, we just want to get one. And we think the ILC, as I've told you before, is the one that's now on track for construction. These numbers are not mine. They come from the ECFA Higgs at Future Colliders study, and you can look them up there. Finally, how can you enter this field and prepare to make these measurements yourself when the time comes for this accelerator to operate? Actually, it's a very opportune time to do that. In the US, the APS-DPF is conducting their community study, SNOMAS 2021. And so we're expecting that many US LHC experimenters are going to dip their toes in the E+E- water and see if it's congenial. Because of the coronavirus, all the meetings are on video. So just set your clock back 8 hours and join us. On this slide, I posted a number of materials that the ILC Physics Working Group has put out there to enable you, the general audience of high energy physicists, to try your hand at ILC studies, learn what the difficulties are, and maybe have your own ideas about how we can do even better than I've shown you on these slides. So we believe it's now time to prepare for this adventure of studying the Higgs boson and other windows into the standard model with high precision. Well, thank you very much for your attention.
Okay, thank you very much, Mikael, for this nice presentation, and also even for your inconvenient time zone for these discussions. Yeah, thanks a lot. We really appreciate it. So, okay, do you have any question or comment for the presentation now? We can use the raise hand features of the Zoom.
Okay, I cannot raise the hand, but maybe I will ask a question.
Okay, yeah, go ahead.
So there is a lot of discussion in this talk about measurement of couplings, but in terms of EFT, differential distribution are always also helping because they are more sensitive at IPT. Are there any kind of studies of this sort on the ILC program or investigation at the moment?
Well, there is a study of differential distributions. Of course, well, there's certainly studies of the differential distributions in Higgs to WW star and Higgs to ZZ star. And if you look in the paper, which is in red on the slide that you're looking at now, there are references to those studies, or write to me, I'll tell you where they are. E plus E minus to Z Higgs has an interesting systematics. What's probably more interesting there than the differential distribution in angle, which is pretty simple, is the polarization asymmetry. And that's a very powerful tool. Actually, Junping Tian is going to talk about that in his talk. So yes, I mean, differential distributions are simpler in E plus E minus than in hadron colliders. And then you can use them as nice tools to extract couplings in a very specific way.
Thank you.
Okay, thank you very much. Excuse me. So since we are already reaching the time, so let's have the further discussion on the extended Zoom rooms for the ILC colleagues.
Okay.
Yes, thanks a lot.
Please download the slides and look back and get the link for that room, and we'll be happy to talk to you later this afternoon, or when I get up, or something like that.
All right, great. And Valerio, thank you very much for the question and discussion. And Mikhail, thank you very much for the presentation. And then let's move to the next discussion. And next speaker is Daniel. And the presentation is for the precision Higgs physics at the ILC and its impact on the detector design.
Yeah,
and
hi.
If you don't mind, please share your camera.
Oh, camera as well. Okay, let me see how to do that now. Okay, let me stop sharing and I'll do my camera. Okay.
Yeah, I can see you.
My screen. Okay, so I think you can also see my slide now.
Yes, perfect.
Okay, so I will start. Okay. So I will talk, as you said, yes, on the impact on the detector design of the physics we can do at the ILC. I think Michael has already convinced you that detailed investigation of, for example, the Higgs couplings can open windows to understand what physics is lying beyond the standard model. In electron-positron collisions, Higgs can be produced via various processes, which are sketched here, which turn on at different energies. So at around 250 GeV, we are dominated by this yellow process by so-called Higgs-Strahlung or associated production. As we go to higher energies, the WW and the ZZ fusion processes come into play here. And then at higher energies of around the 500 GeV, we start to get sensitivity to the top quark Yukawa process in green, and then also to the Higgs self-coupling at 500, and then later at higher energies of 1 TeV. So in order to get a full view of the Higgs boson, we have to, at E plus E minus, we have to use this range of collision energies. And the detectors we design for the ILC are designed with this in mind. The ILC we already heard about, so electron and positron collisions starting at 250 GeV, but upgradable in energy to first maybe 500 GeV and then to 1 TeV or beyond. The beams are longitudinally polarized, and the main NINAC uses a superconducting RF technology. A possible run plan would look like this, where over the first maybe 11 years of the program, we get around 2,000 inverse femtobarns of data at 250 GeV in different polarization combinations. Then there's an energy upgrade to, for example, 500 GeV, and we would take around 4,000 inverse femtobarns of data at 500 GeV with an extra relatively small amount of data, the TT bar threshold around 350 GeV. Then beyond this, one can think of upgrading the machine to higher energies of 1 TeV or above. The interaction point of the ILC will be shared by 2 detectors, and 2 groups are now studying detector designs for this. I give links to their talks at ICHEP here on this slide. So I'll talk a bit about the motivations behind these detectors and what detector performance we need to study the Higgs boson with the precision we want. So first I want to discuss tracking of charged particles. So to understand the requirements for tracking, we look at this Higgs-Strahlung process again here. Since we are an electron-positron collider, we know the initial energy and initial form momentum of the electrons and positrons rather well. So it's a nominal energy plus some beam energy spread and beam Strahlung, which give us a spectrum of collision energy you see on this graph in the middle of the page. So there's some relatively narrow peak, which is due to the intrinsic width of the beam energy spectrum, and then this tail to the left, which is due to the energy loss due to beam Strahlung as the bunches pass through each other. So we know the initial state and form momentum rather well, and we will measure the momentum of this Z boson using our detector. By subtracting green from blue, we can then infer the form momentum of the recoiling system, in this example, the Higgs. How well we can measure its form momentum depends both on this beam energy spread effect from the initial state and on the precision with which our detector can measure the Z. So this consideration defines how well we have to measure the Z using our detector. So the smearing due to the detector should not be larger, should not dominate that from the initial state. Neither does it have to be much better than the initial state spread. So this defines the momentum resolution we want our detector to have, which is a few times 10 to the minus 5 on the momentum of charged particles. Here's an example, well, here's a bit more details how this works. On the left, you see an event display, such an event where the Z has decayed to 2 muons and the Higgs has decayed invisibly. And then if we look at the mass recoiling against these 2 muons, we get this plot in the middle of the page, where we have a background mostly from ZZ production and this sharp peak from the Higgs signal sitting on top of it. From this peak, we want to extract essentially 2 things. One is the area of the peak, which is related, of course, to the cross-section for the Higgs-Strahlung process and is sensitive to the strength of the HZZ coupling. Then the position of the peak gives us, of course, the mass of the Higgs boson. How well we can measure these 2 depends on how wide this peak is. So the width of this peak drives the precision with which we can measure these 2 quantities. And as we said before, this depends both on our detector, the momentum resolution we can achieve, and on the initial beam energy spread from the ILC. So our 2 detectors, SID and ILD, have taken different approaches to achieving this resolution. So on the left, SID has chosen an all-silicon tracking system, where in addition to the vertex detector at the very center, there are 5 layers of silicon strips, giving a relatively small number of very precise hits along the particle trajectory. On the other hand, ILD's tracking detector is built around a large TPC, a gaseous time projection chamber, complemented with a number of silicon detectors both before and after it. Both of these approaches have been shown in very detailed simulations to achieve the required performance you can see on this plot on the bottom of a momentum resolution of a few times 10 to the minus 5 at high momentum. Next, I want to move on to vertexing for Higgs. So this is, for the point of view of Higgs, is mostly important to study the different hadronic branching ratios. So the idea is to measure the partial cross-sections of Higgs strahlung with Higgs decays into BB, to charm, or into gluons. We can combine these partial cross-sections with a total measurement we've made using the Higgs strahlung technique I just talked about to get a direct measurement of the absolute branching ratios. So separating these hadronic flavors depends, of course, on B and C jet tagging, which uses displaced vertices, displaced tracks, and also secondary leptons coming from heavy flavor decays. These plots show how such an analysis can work. So these bottom three plots are templates in a two-dimensional space of B likeliness versus C likeliness. These are the outputs of some multivariate analyses. And you can see the distribution of events in the three classes of events is very different. The BB bar has a strong peak at the bottom right, CC bar top left, and the gluon on the bottom left. So by fitting our data on the top with some sum of different flavor templates, we can extract these partial cross sections. Typical precisions we can achieve around 1% on in the BB case, around 8% relative uncertainty for the charm, and a similar uncertainty for the gluon decays. So how does this, what part of the detector is needed for this? This, of course, is dominated by the vertex detector, where the key aspects are an excellent position resolution. So we need sensors with very high resolution, better than 5 microns. The vertex detector must be as close as possible to the interaction point. How close we can go is dominated by machine backgrounds. So that is shown on this bottom plot here. So as the bunches pass through each other, a large number of low energy electrons and positrons are produced, which are constrained by the rather strong solenoid of the detector. So that constrains the electrons and positrons into this sort of cone shape you can see here. So on this plot, the left-hand center of the left-hand side is the interaction point. And you see this sort of cone of electrons and positrons coming out. So our vertex detector should not enter into this high density cone. So by placing it around 1.5 centimeters from the beam pipe, from the interaction point, sorry, is a safe place to be. Finally, I want to discuss the calorimetry for Higgs measurements. So the majority of final states will decay into hadronic jets, so of W and Z as well as of Higgs. So here the key figure of merit we want to achieve is to be able to distinguish different hadronic final states, so distinguish the decays of W and Z and also Higgs to hadronic jets. And to do that, we have to be able to measure jet energies very precisely. We do that using this particle flow technique, which is based on this plot on the right. This right-hand plot shows a fraction of a jet's energy, which is carried by either charged particles in red, by photons in blue, or neutral hadrons in pink. The charge component is, of course, measured by the tracker with excellent resolution. So this, on average, corresponds to around 65% of the jet energy. And the calorimeters are needed only to measure this photon component and the neutral, even smaller neutral hadron component. So this sounds like the calorimeter has not much to do, but however, the calorimeter must be able to see what energy deposit is coming from a charged particle and what is coming from a neutral particle. So to do this, three aspects are particularly important. One is to have a calorimeter with very detailed readouts, so we can get a clear image of the calorimetric showers coming from the various particles inside a jet. So this picture in the center here is a simulation of a multi-jet event. And the granularity we need is typically less than one readout channel per cubic centimeter in the ecal, and maybe around 30 cubic centimeters in the hadronic calorimeter. In order to understand all of this wealth of information coming from the calorimeters, we need sophisticated reconstruction algorithms. One of the best we have at the moment is this Pandora PFA, which the results of which are shown on this plot on the bottom left. So here we look at the dijet mass reconstructed from full simulation of this sort of multi-jet events, where we can see a nice separation between the hadronic decays of the W and the Z bosons. Finally, in order to make this work well, we need to have as little material as possible before particles reach the calorimeters in order to make this pattern recognition easier and even possible. So in order to address that, both the electromagnetic and hadronic calorimeters are placed within the solenoid of the detector. So what does this allow us to do? So this is an example of looking for invisible decays of the Higgs boson, again in this Higgs-Stralsund process, where we look for cases when the Z decays hadronically. This, of course, is a majority of cases. So in order to maximize the sensitivity, we look at this channel. So on the left-hand picture here, we see the mass recoiling against this hadronic Z decay. We can see the various backgrounds in colors. And then this red component would be what a 10% invisibly decaying Higgs would look like. So on this plot, you can see it's rather, the 10% level, it's trivial to find such a bump. Left-hand plot is at 250 GeV. We look at 500 GeV as a plot on the right. You can see it becomes more challenging because of various different reasons, in fact. But even here, one can extract this excess of the events from invisible Higgs decays. As an illustration of how important the jet energy resolution is on that, this bottom right-hand plot shows on the y-axis the upper limit one can get on such invisible Higgs decays for this 500 GeV case, and sees how it depends on how well the jet energy resolution, how good the jet energy resolution is. So one on this axis is our standard detector in ILD, and as we decrease the resolution, for example, by 40%, we will get to this 1.4 place. So you can see there's a significant contribution of the jet energy resolution on our sensitivity to such invisible decays. Putting everything together, all the different energies together, we can achieve limits on invisible Higgs decays, the order of a fraction of 1%. So in summary, for the detector requirements for ILC, so we need this excellent charged track momentum resolution of a few times 10 to the minus 5 in order to measure the Higgs mass recoil to get the total cross-section and total coupling to the Z boson. The impact parameter resolution for charge tracks should be of the order of a few microns to allow the identification of B, and in particular charm and tau decays, the more challenging cases. And the hadronic jet energy resolution must be of the order of a few percent, maybe between 3 and 5% over a rather wide energy range, which we expect to see at ILC. In addition to these requirements coming from Higgs physics, we should also have a hermetic, almost completely hermetic detector, cover almost all the solid angle, particularly to look for searches for new physics with missing momentum signatures. So the ILC, together with
Daniel, it's already 15 minutes already passed, so let's wrap up.
I have yes, only 1 or 2 more slides. So the ILC, together with its detectors, will allow such nicely high precision measurements of the Higgs sector. We already saw this plot before, comparing what ILC can achieve compared with when it combines its results with high Lumi L8Z. And this will hopefully, this will help to point the way to physics beyond the standard model. So that's the end. So I just remind you of this discussion session we will have later today. Thank you.
Okay, Daniel, thank you very much for the nice presentation. And now let's start the discussion. And could you please raise your hand if you have a question or comment for Daniel's presentation?
So I might have a quick one, if possible. Since you emphasize the coverage as one of your requirements, could you tell a bit more what is the actual maximum pseudo rapidity angle that the detectors are planning to cover, both in either calorimeter or tracker?
So in the tracker, it goes to around 5 degrees. We work in degrees rather than pseudo rapidity, so I can't translate that immediately to pseudo rapidity. And for the calorimetry, it goes much further down. I can't remember the exact number, but there's a hole of around 2 centimeters radius, around 2 meters away from the interaction point.
Okay, thanks. Now we'll go and do the calculation. I will try.
Okay, so thank you very much for the discussion and the presentation. Let's now move to the next presentation.
Sorry, there is a question. Somebody raised his hand.
I just wanted to ask, are the costs of the two detectors the same?
The costs are, we've made a rather detailed costing. The costs of the two detectors are not quite the same. So the ILD is rather larger and is therefore also rather more expensive, but they are, okay, according to current projections, they're within a factor 2, let's say that. The difference is smaller than a factor 2.
Oh, smaller than that.
Yeah. I can't remember the exact ratio, but I guess somewhere between a factor 1.5 and 2.
And what's the unit?
This is just the factor, the factor between them, the ratio between the costs. So,
do you have an idea about what their costs actually are?
Yes. So, okay, of order $500 million.
Okay, very.
That's also so similar to an LHC detector.
Okay. Thank you.
Okay, thank you very much. So then let's move to the next presentation. Yeah, thanks a lot. The next one is presented by Tamoy, and the talk about the search for light boson via Yukawa process at lepton colliders. So could you please share the slide from you?
Yes. Can you hear me?
Yes, and I can see your slide as well.
Okay, thank you. Okay, so hello everybody. Already we have heard very nice talks about how LHC will be very nice for a Higgs precision measurement. With precision measurement, it can give us some idea about BSM models. So now I will talk about prospect of LHC for directly searching any motivating BSM scenarios. For example, I will talk about a light scalar or a pseudoscalar which can be probed at ILC. So we know that BSM models often involve extended Higgs sector. For example, the gauged T1b minus L model or basic some dark matter models introduce a scalar singlet along with the standard model doublet. In MSSM, we have 2 scalar doublets and it is a 2 Higgs doublet model. And the left-right symmetric model or type 2 seesaw usually have a scalar triplet along with the standard model Higgs. And so BSM usually involves extended Higgs sector, and 2 Higgs doublet model is one of the simplest extension of the standard model. And I'll talk about type X 2 Higgs doublet model, which is one of the 2 Higgs doublet model in terms of the Yukawa couplings. And in this model, it is possible to reconcile the long-standing muon G-2 anomaly using a light pseudoscalar. And I'll discuss how to look for such a light pseudoscalar at the ILC. So let's look into the model. So this is the scalar potential of the 2 Higgs doublet model with 2 scalar doublets, phi1 and phi2. And the masses of the new scalars, which are 1 CP even Higgs, 1 CP odd Higgs, and the charge scalar are written here. So as you can see, if lambda 5 is very close to negative of lambda 4, then we will have a mass spectrum where the pseudoscalar will be very light compared to the heavy CP even Higgs or the charge scalar. This is the spectrum which will be interested. And the type X name come from the Yukawa structure, where the quark sector couples to one doublet, which is phi 2, and the leptonic sector couples to the another doublet, which is phi 1. And this is possible due to this Z2 symmetry, under which phi 1 and the right-handed singlet leptons are odd under this Z2 symmetry. So after symmetry breaking, we will have this kind of structure where we will have an extra Yukawa modifier along with the standard Yukawa, which is mass over the wave. And the Yukawa modifiers for this model are written in this table, where alpha is the mixing among the CP even scalars and beta is the wave ratio. So one interesting thing is the lepton Yukawa coupling modifier, which is minus sine alpha over cos beta. As you can see from this table, this is the lepton Higgs Yukawa modifier. And it can be written as a function of beta minus alpha and tan beta. So from the Higgs data, we already know that the Higgs vector boson couplings are very close to 1, which makes sine beta minus alpha very close to 1. And also H tau tau coupling is also very close to 1, the absolute value. So there are two possibilities in this scenario, where in one case, the tan beta cos beta minus alpha is 0 and sine beta minus alpha is very close to 1, which we'll call the right sign limit, where H tau tau coupling, Yukawa coupling will be +1. And in another scenario, where tan beta and cos beta minus alpha will be very close to 2, which makes the tau H coupling -1, which is the wrong sign limit. So in this case, the wrong sign limit will have H tau tau coupling negative, -1, and all the quark coupling to +1. So now let's look at the constraints and the muon G-2 in this model. So we know the muon G-2 has experimental value and theoretical value does not match precisely. So the theoretical value has different components from QED or electric, vacuum polarization, and the light by light scattering. And the contribution from different theoretical values are written here. And the difference between the theoretical and experimental value is 27 plus minus 7.2 in terms of 10 to minus 10. So you can see that the difference is very close to what we have in the electroweak sector. And this is an extra motivation to look for reconciling the anomaly in the electroweak new physics. So in 2x doublet model, the muon G-2 can appear via these two diagrams. One is one loop and another one is a two loop. In one loop, we will have a Higgs exchange or the charge Higgs exchange. And in this case, the contribution from CP even Higgs at one loop is positive and the CP odd scalar contribution is negative. Since we need a positive contribution, then at one loop, if we want to explain the muon anomaly, the CP even new Higgs has to be less than 5 GeV, which is not possible, already ruled out from other several experiments. So it is possible in this model to go to the two loop level. The Bargy two loop contribution will be enhanced for large tan beta and light pseudoscalar with a top or bottom or tau loop. So this is the plane which plane in MA tan beta plane where we can explain the muon G-2. The blue region, green region is at 1 sigma and the yellow is at 2 sigma. And the red and the blue lines are coming from constants from lepton universality. So you can see that this is the region which can explain the muon anomaly. So that corresponds to MA should be less than 60-70 GeV, but tan beta should be very high, around 50 or so. So now I'll talk about how these constraints are coming. So these lepton universality constraints are coming from mostly from these two measurements, this tau going to mu and tau going to electron, or the ratio of tau to electron and mu to electron. Because of additional new charge scalar or the new neutral scalar, these diagrams will modify this ratio. And from the heavy flavor averaging group, we get that the tan beta should not be very large. So it limits tan beta from up to 60 or 70. So the constraint from signal strength measurement at LHC is also another important constraint. So here is the plot from G-Fitter collaboration in cos beta minus alpha tan beta plane. So as you can see, the cos beta minus alpha will be very close to 0, which corresponds to sin beta minus alpha very close to 1. And also, apart from this cos beta minus alpha exactly 0 range, there is another different region which is also satisfied. This is the range where cos beta minus alpha times tan beta will be very close to 2, which is the wrong sign Yukawa limit. So still from LHC measurements, the wrong sign Yukawa is still allowed, and we'll be interested in this region. Another important constants usually comes for 2 Higgs doublet model is from B2S gamma or BS2 mu mu from these diagrams. So for type 2 Higgs doublet model, which is the MSSM scenario, the B2S gamma has an enhancement in this coupling with tan beta. But for type X, both the couplings are decreased by a factor of tan beta. Similarly, for BS2 mu mu, we will have for A or H going to mu mu coupling, there is a tan beta enhancement. But for the quark sector, there will be 1 by tan beta, which makes it nearly independent of tan beta. But for type 2 Higgs doublet model, this will be enhanced by tan beta square. So that's why the constraints on type 2 is very strong. So for type X, this is the limit from the same G-Fitter collaboration. And as you can see that for any values of charge Higgs mass, the limit on tan beta is 3, which is very small. So the light pseudoscalar of 50-60 GeV and large tan beta is still very much allowed from all the experimental constraints. So now I'll move into how to look for such a light pseudoscalar at ILC. So one possibility is to have this Higgs-Starling of Z going to H and A, but in this model, this Z-HA coupling is proportional to cos beta minus alpha, and since we know that cos beta minus alpha is very close to 0, this model, this channel is not possible. Also, this Z going to heavy CP even Higgs and a pseudoscalar may not be feasible if the heavy CP even Higgs is heavier than 200 GeV. So one possible option is the so-called Yukawa production, where we will have a pseudoscalar radiating from a tau, which will again decay to a pair of taus, which gives a 4 tau final state. And this is equivalent to TT-var H searches at LHC, which is the independent probe of Yukawa structure without any other, depending on masses of heavy other scalars. So at ILC, since we know all the 4 common components of energy momentum, we can reconstruct the 4 taus using collinear approximation, and this will enable us to measure the mass of the light pseudoscalar also. So here is the signal cross-section as a function of mass of the pseudoscalar for different values of root S and different values of tan beta. The solid line is for tan beta 60 and the dashed line are for tan beta 40. And also we are considering the polarized beam. So as you can see, the cross-section is order of few femtobarn range, which is quite large for ILC. So the dominant background for this process will come from ZZ to 4 tau. Also, there will be some contribution from ZZ to 2 tau 2J final state from J as misidentifies as tau. And also this standard model Higgs production will also be a background for us, which is ZH going to 4 tau. And the total partonic cross-section will be around 6 femtobarn, and 2 tau 2J cross-section is very large, but misidentification will make it very small. So this is the way we can look for ILC light A at ILC. So this is the standard procedure. We go to MATGRAPH, then Pythia. After that, we'll go to Delphis with ILD card. And we need at least 3 tau jets, and along with another object which can be tau jet or an on-deck jet or a lepton. And all should be having minimum energy of 20 GeV. And it should be in the central region, which is cos theta should be less than 0.98. That corresponds to mod pseudo rapidity should be less than 2.3. For tau tagging efficiency, we choose 2 tagging efficiency. One is 60%, which is typical for LHC phenomenology study. And since ILC is a much clean scenario, we took another 90% tau tagging efficiency, which will be hopefully possible at ILC. For misidentification, we take 0.5% for both the scenarios. So now we will have 4 taus at the final state, and we can use collinear approximation to reconstruct the taus. If collinear approximation is valid, if the taus have high enough energy so that the decay products of the tau will be boosted. So the missing energy component will be along that visible component. So then we can solve this energy momentum equation for all the 4 components. And in that case, we can calculate what is the tau momentum, and then we can reconstruct the masses. So here is the strategy for reconstruction. So we'll have 4 tau jets, and I'm denoting here tau 1, 2, 3, 4, and in terms of this energy ordered value. So the highest energy tau, which is tau 1, is unlikely to come from the pseudoscalar because it can come from that Z, which does not radiate A. So energy for a 3-body phase space can go up to very close to root S by 2, which is true for the pseudoscalar. So we assume that the highest energy tau will not come from the decay of Z. So now we move to remove the tau, and we have 3 taus, tau 2, 3, 4. And from these 3, we will have 2 possible opposite sign combination. So let's say 2, 3 and 2, 4 are the 2 possible opposite sign combination. And then we chose the combination which gives highest PT, and that is most likely to come from the decay of A. So if we have 2, 3 combination has a higher PT than 2, 4 combination, then we'll just check 2, 3 as the taus which are coming from the decay of pseudoscalar. So we construct the invariant mass from these 2, 3 component and denote it as an MA, which is reconstructed. And the other combination we are denoting as M other to see whether this strategy works or not. So here is one simulation of this reconstructed pseudoscalar mass and the M other using our strategy. This is done for MA of 40 GeV and 10 beta 50, which satisfies the muon G minus 2. And this is done for
have 2
ILC.
more minutes.
Yes. So ILC 250 with a 2000 femtobarn inverse. So as you can see, the signal, which is the blue pixels, are very close to 40 GeV, which is what we expect. And M other, which is the other combination, is spread from 20 GeV to 120 GeV. So this explains how whether this reconstruction of MA Reco is truly the pseudoscalar or not. So which tells us that this works, and the background, which is the red pixels, are always very close to 90 GeV, which because these are coming from mostly Z. So now this is for MA 40 GeV. So if we plot the histogram for different values of MA, we can see that we'll get a nice peak of reconstructed pseudoscalar mass as a function of normalized events. And the black is the background. And for MA 90 GeV, signal and background coincides. So you can see that we can have a very nice mass reconstruction in this way. So here is a typical table, cut flow table for this scenario. At the pre-selection level, we can see that the significance is more than 5 sigma, but with better mass reconstruction, we can even increase the significance also. So this was the reach of ILC 250 for this model. So this is done for tau tagging efficiency of 60%. So red lines are for 2 sigma, blue are for 5 sigma, and solid lines are with 2000 femtobarn inverse, and dashed lines are for 500 femtobarn inverse. So as you can see that even with 500 femtobarn inverse ILC 250, we can explore most of the parameter space, which can explain the muon G minus 2, which is denoted here in this yellow range. So now if we move to even better tagging efficiency of 90%, then this blue line, which is 5 sigma significance, move to this line to that line when we take the efficiency of 90%, which will explore almost the full parameter space in this model. So in conclusion, a light pseudoscalar can explain the muon anomaly, and due to hydrophobic nature, it is very hard to test this model at LHC or the pseudoscalar at LHC. And lepton collider is very ideal for this model, and we can utilize the Higgs factory for testing this light A scenario independent of the mass scale of the other scalars. So it should not be, may not be from type X or any other model, but we can have an independent search for this kind of light pseudoscalar. And it is possible to reconstruct the mass of the resonance using collinear approximation. And 500 femtobarn inverse is enough to explore the relevant parameter space, which can explain the muon anomaly. Thank you.
Okay, thank you very much, Tamoy, for this interesting presentation. So now we can discuss the question comment. So does anybody have a question or comment for the presentation? Okay, Tanya, go ahead.
Sorry, I couldn't see that I raised my hand, but apparently I did. I have a question for your title. I mean, in your title, you have pseudo in brackets. So did you also test this for a non-pseudo pseudo scalar?
No, so this we have explained, analyzed the model for a light pseudoscalar, but this can be true for if we have a heavy light scalar which have this kind of structure also.
Yeah,
That's
but the
why.
coupling, I mean, the coupling to the fermions is different. So the question is whether
Yes, for type X, it is not possible. My point is that for if we have any light scalar which mostly couples to tau, then this strategy will work.
Okay. My question is whether you wouldn't expect different distributions, you know, partial for
in principle, because of the CP, there will be different distribution, but the CP structure we have not used. So for this strategy, it will not change. But if we have a light scalar or pseudoscalar, for that we have to do different study that we have not done.
Oh, yes. Okay. All right. Thank you.
Thank you, Tanya. Okay, so is there some other quick question? Okay, I have a quick question then. So are you plan to study the BB tau final state as well?
Yes, so BB tau final state has already been studied for type 2 to Higgs
Okay.
doublet model. Yeah.
Okay, thanks a lot.
But type X BB tau is not very large because A going to BB coupling is very small because of the tan beta suppression.
Okay, that's I need to think. But okay, thanks a lot. Okay, yeah. Then let's move to the next presentation, and next one will be presented by Jumping, and yeah, the title will be a new way of understanding the role of each measurement at future Higgs factories in SM-EFT.
Okay, I hope you can see me as well as the slide.
Yes. Yeah,
good.
Perfect.
Yeah, I'm Junbin Chen from the University of Tokyo, and I will be talking about a new way of understanding the role of each measurement in global standard EFT fit at future lepton colliders. So I'm talking on behalf of my collaborators, Michael and Kisk. Both of them are here, I think. Sorry, I cannot. Okay, so assuming the scale of new physics is sufficiently above the electroweak scale, all the standard model measurements in the Higgs sector, top sector, or electroweak sector can fit into a standard model EFT framework and provide a coherent test of BSM physics. Practically, a global EFT fit involves many fitting parameters and many input measurements. The accurate understanding of roles of each measurement become often difficult. Over the past few years, focusing on the impact on Higgs coupling determination at future E minus, the roles of electroweak precision observers, triple gauge coupling, beam polarizations, as well as top core electroweak couplings get highly recognized, but it is still clear enough. So in this talk, I will first give a brief recap on both qualitative and quantitative understanding, and then introduce a new way of a more transparent understanding. So I will follow the EFT formalism as already introduced by Michael earlier in this session, based on the Warsaw basis, and was adopted in the previous global EFT fit in this paper. So in total, there are actually 22 parameters, and many of the parameters, they have relatively simple relations with the measurements. So I will focus on only a small subset, and the 7 operators are listed here, which can represent the most of the non-trivial relations. So the CH is related to the interaction of Higgs field only, and the second category has CHA, CHA prime, CHE. They are related to the Higgs current and the lepton current contact interactions, and the another category is CWW, CWB, and CBB. They are related to the interaction between the Higgs field and the gauge field. So let me start with the CH operator. So this has something to do with the determination of absolute Higgs couplings and the role of a unique role of the inclusive cross-section measurement. So this operator will generate a kinetic term as shown here, and to renormalize the standard model Higgs field, so we have to rescale the Higgs field by this factor. And as a result, all the standard model Higgs couplings will be shifted uniformly by a factor minus CH half. So this, because of this uniform shift, so CH, the effect of CH will cancel out in the Higgs branch ratio or ratio of couplings. So CH has to be determined using inclusive cross-section measurement, such as E plus minus to Z Higgs, which is enabled by the Ruckelmann's technique at E plus minus, as introduced earlier by Daniel. It's worth mentioning, so the uncertainty of this CH parameter essentially defines the end precision one can achieve for the Higgs ZZ or Higgs W couplings. So moving to the second category, the CH-AR operators. So this has something to do with the role of electroweak precision observers. So this set of contact interaction operators will generate corrections to these three diagrams. And notably, in the middle, this diagram is E plus minus 2 Z Higgs, the dominant Higgs process. And in the right side is exactly the Z-port process. So immediately, we will recognize the electroweak precision observer at Z-port can help a lot to constrain this operator, hence helping the Higgs coupling determination using the Z-Higgs process. And in particular, the observer like left-right asymmetry and the partial ways of Z to leptons. So on the other hand, so the Higgs process actually can probe the same type of interactions. So, and in particular, the correction to this process grows as an S of mz squared. So the Higgs measurement can actually also help the measurement of the Z-port physics. But this is only possible when there will be a multiple measurement of this cross-section. I will come to this point later. So moving to the third category, the CWW type operators. So this is a place where the synergies with the Higgs measurement at LHC take place. So this type of operators will modify the interaction between Higgs and gauge bosons. So either Higgs to gamma, gamma, gamma Z, or ZZ, or WW. And this correction is at true level. So interestingly, at standard model, the Higgs to WW and the Z, gamma Z, Higgs to gamma gamma and the gamma Z are loop-induced process. So as a consequence, this correction from this operator will generate a relatively very large effect on, for the, in particular, the Higgs gamma gamma and the gamma Z. As you can see from the relative corrections on the partial ways here, the large coefficients in front of this CW type operators for Higgs to gamma gamma and gamma Z. So, and the distal process, since the branch ratios are rare, so the LHC can do a very good job. And moreover, if we can use the ratio of the branch ratio of this two normalized by Higgs to Z star, then the measurement I defined as R gamma gamma or gamma Z, this will be even better because we will be able to actually cancel out many of the systematics and also remove the model dependence in the LHC measurement. So this two measurement will give two very strong constraints on this three operator, and together with another actually triple gauge coupling, we will resolve fully these three operators. So now I'm prepared to explain the role of beam polarizations, where all of the operators that I introduced so far come into play together, actually. So these are the diagrams for the E plus minus to Z Higgs allowed in the EFT. So, and I indicated the vertex here, red and blue, from the operators, CWW or the CHI operators. So why the polarized cross-section measurement can help? So let's look at the dependence of the correction to the polarized cross-section on these EFT operators. So first of all, so they all relate to a uniform shift, as I introduced earlier, CH, and the most important thing, first of all, we would like to use from the cross-section measurement of the Higgs is to actually determine this CH. But on the other hand, this cross-section will also depend on the other EFT parameters. So in order to get as precise as possible the determination of CH, then we have to actually control or constrain the other EFT parameters sufficiently well. So the interesting here is if you compare this dependence on the CWW and the CHR for the unpolarized case. So this is for the unpolarized case, and this is the right-handed polarized electron, and this is the left-handed polarized electron. So you see the right-handed cross-section has much weaker dependence on CWW and the CHR. So this is not surprising because the carrier new physics effect will be suppressed with the right-handed electron. So that means with the right-handed cross-section measurement, we will be able to determine the CH much better. And on the other hand, once this CH is determined, since the left-handed cross-section depends strongly on the other EFT parameter, the CWW, then we can use the redundant measurement of left-handed cross-section and further improve these parameters. So I will show in next page some numerical numbers. So these numbers are presented the uncertainty of the EFT coefficient, and in various scenarios at the 250 GeV. So first of all, as a reference, so assuming no polarization and still with 2 image antibody data. So and you can say the uncertainties on those parameters, and these numbers are in unit of 10⁻⁴. So they are typically already very small, but the CH is still at a percent level. So look at the second row. If we replace the 2 image antibody data by pure right-handed polarization, then you can say, so the immediate big improvement is on the CH. So as I explained in qualitatively already in the previous slide. And then if we split this 2 image antibody data to half the left-handed polarized and the half right-handed polarized, then we can say, so the CH parameters actually get significantly improved. So there's also improvement on the CWW and the CHE. So this basically explains or supports what I explained in the previous slide. And I leave you for fun to say the effect of another scenario, the pure left-handed data or with even more unpolarized data. So far, the way of evaluating the laws of measurement is still classical, and one can find many more examples in the literature as sketched in the bottom 2 plots to evaluate the impact of the improved TGC at future E+- comparing to the lab, or with the additional improved ZIPO measurement with either dedicated ZIPO run or retrieve return. So we can always say the overall impact, but this way, so we can only basically vary one certain set of input measurement, and then say how another set of precision Higgs couplings vary. So we can understand basically the synergies between 2 measurements. So it's very hard to figure out the synergies among multiple measurements, how they play together. So this motivates us the study of a new way for more transparent understanding. Basically, a new idea to answer the question: can we solve the global field analytically? So more explicitly, we would like to express the uncertainty in a Higgs coupling, which we are interested in, analytically in terms of the uncertainties in observers. So some toy illustration is something like this. Let's say in the end, some uncertainty of interest in the coupling can be expressed and analytically and as a function of the measurement uncertainties. And was pointed out, so in this way, so all the quantities here are defined in a physical basis. So this should be EFT basis independent. So this is also a nice feature. So and to get this expression, so as an intermediate step, we must get first the expression for the uncertainties in Western coefficient, which are the direct fitting parameters. So let me
we have
first
2 more minutes.
Okay, so and then I should go very fast. So the basic notations, so the Ci are basically the fitting parameters. So we have n, assuming we have n number of fitting parameter, and the y are the observers. So if assume we have m a number of observers and already expressed with in terms of deviation with respect to standard value. So basically the parameterization of observers can be simply written down in a matrix form, y equals to VC, and this coefficient Vij are obtained from the series computations, and as we know. So and then to do the global fit, we further need the measurement covariance matrix. I call it EY. So this can be diagonalized with in form like this. So then to do the global fit is basically to minimize this chi-square and to replace the observer by the Western coefficient using this V matrix, and we immediately obtain the chi-square defined by the fitting parameters. And then this D matrix is exactly the inverse of the covariance matrix of fitting parameter. So and the element of the matrix D can be written down in form like this. And the important thing is here is this we want to keep analytical dependence on this measurement area delta K. So doing global fit is equivalent to invert this matrix, but now we want to keep the analytical expression. So the numerical solution is already done in the previous papers. So for the simplest case, if m equals n, that means there's no redundant measurement. So then every matrix in this D, so actually n by n matrix, so everyone is invertible, so it's very easy. So we just invert this D and by this, and the inverse of the V matrix can be calculated simply, and we can leave out the expression of the measurement area here. So as an example, so there's actually very useful example for this non-redundant case, and so that is for unpolarized E plus minus I250, almost no redundant measurement. And what we can get is from this equation, or the inverse the matrix is basically the covariance matrix of the C parameter, and then we can also obtain the uncertainty of the Higgs couplings. And then so as a result, they can be written down in terms of the uncertainty of those various measurements. Actually, you can say they depend on not only 1 or 2 or 3 measurements, depend on many measurements. And then we can plug in the prospective uncertainties of each measurement, and you can say which actually measurement is still the limiting factor. So and you can say here there are many limiting factors other than naively we thought this cross-section measurement. Actually, the electroweak precision is most of them. So that's why for unpolarized E plus minus we really need the Z-pole much more than the polarized one. And the TGC and the branch ratio of Higgs to gamma Z, they are all important comparing to the measurement of cross-section of the Higgs. So so before I move into the most general case, so we can slightly rewrite the solution of this special case equals n. So this is basically a quadratic sum of each measurement area, and this can be basically abstract as a form like this. But there's few summations, and I will explain later. But it turns out for the most general case, if we have more redundant measurement, we just need to slightly modify the number of measurement in this formula. And this is the formula for, and we found, and it exists first of all, and this is the exact formula. We can get the covariance matrix, and this is the uncertainty on any of the Wilson coefficient data squared and expressed by two parts. So first of all, let me explain what is the how the summation runs. So it runs over the A or S. A is basically defined by a combination of the from 1 to m. So you select n numbers or n measurement from the n measurement. So this is the physics meaning of the air. And once the
excuse me, we need to wrap up soon.
Okay, I think I'm in the last slide. So this air will define actually the matrix V air. So V air is a subset of the V and formed by the n rows. And also define the data air here is the product of the measurement area defined also by this n measurements. And S is just one less measurement. So, but certainly non-trivial is the VSI. So since the V matrix originally is m by n. So if we select n minus 1 rows, we still have to eliminate one column. So this is the column I will be eliminated. So okay, so I think I will skip the summary just to let you know. So there will be more studies to apply this general formula for the redundant case, and in particular, I'm interested how we can write down the analytic expression when beam polarization or multiple central mass energy and multiple Higgs production are present. Thank you very much for attention.
Okay, Junpin, thank you very much for the presentation. And yeah, if you have any urgent and quick question, please raise your hand. Okay, so will you be also in the ILC Zoom room in this afternoon, right?
Yes,
okay,
I will be there.
Okay, yeah, please go there for the further discussion. And yeah, thank you very much for your nice presentation again. And let's move to the next presentation given by Lorenzo about the Higgs physics possibility at the muon collider.
Can you see me and the presentation?
Perfect.
Can you see also my arrow moving?
Yes, yeah, I can see that.
Okay, thanks. Okay, good morning or good afternoon, depending on the time zone. I'm Lorenzo Sestini, and I'm going to present the Higgs physics possibilities at the muon collider on behalf of the International Muon Collider Collaboration. So we already see this in the previous talks. One of the goals of the future colliders is to push our knowledge of the couplings of the Higgs bosons with the standard model particles below the 1% precision scale, and this will allow to test several new physics scenarios. Another aspect of the Higgs physics is the Higgs potential. Well, the Higgs potential rules the electroweak symmetry breaking and the generation of the mass. Up to now we just know the first term, the mass term of the potential, but the trilinear and quadrilinear coupling are not known experimentally. So we can say that the physics of the electroweak symmetry breaking is experimentally unexplored. We have several expectations from the experiments at the future colliders on these parameters. For example, click with 5 inverse aptobarns at 3 TeV can measure the trilinear coupling with an uncertainty of -7% and plus 11% using double Higgs events. In this conference, I have also seen better estimation than this, so they can improve even with even this uncertainty. Concerning the quadrilinear coupling, FCC-HH expect to measure the quadrilinear coupling using triple Higgs events in this range at 68% confidence level between -2 and +13 times the standard model. Also, it is a quite large range. So the muon collider can be the dream machine for the Higgs physics measurements. There are several reasons for this. First of all, we have clean events as in positron-electron colliders. then we can also achieve high collision energy as in hadron colliders, because we have very low radiation losses with respect to the electrons. And that multi-TeV muon collider is equivalent to a WW collider, since most of the events are produced through WW fusion. So it will be possible to produce high yields of X, double X, and triple X, as you can see here from this plot where I show the cross-section as a function of the center of mass energy of the muon. Very challenging, but it is gaining momentum because you can see at ICHEP this year we have other talks, for example, on the muon cooling, on the accelerator complex, on the machine detector interface, and also on the detector, and this one. So what are the muon colliders' advantages with respect to the other future machines? In this plot here, you can see the production as for a muon collider 3TeV. You can see that the cross-section for the muon collider is higher at the same center of mass energy. This is due to the different initial state radiation. For this reason, at the same center of mass energy, the muon collider has a better sensitivity with respect to the Higgs self-coupling with respect to an electron-positron collider. Then we have also first phenomenological studies that show that at 14 TeV with 33 inverse aptobar, the muon collider can measure the quadrilinear coupling with an uncertainty of 50%, as you can see, for example, in this plot here. But you have to consider also the detector effects on these kind of measurements, because these are just phenomenological aspects. So in a muon collider detector, there are several challenges. This background is produced by the decays of muons that circulate in the beams, and they generate decaying electrons, positrons, and neutrinos. And the interactions of these particles with the machine and the machine detector interface can produce other particles, secondary particles like photons, neutrons, or hadrons. You can see, for example, this distribution generated with this software Mars 15. This has been generated at 1.5 TeV of collision energy by the MAP collaboration, the Muon Accelerator Program collaboration. We are also working to produce the background at higher collision energies, and you can see also you can see how we plan to produce this background in this talk by Francesco on the last Wednesday. By the way, this background poses limitations, could pose limitations on the physics reach. So the detectors, the machine detector interface, they have to be developed in order to mitigate the background. For example, the Muon Accelerator program proposed to put 2 tungsten cone-shaped nozzles near the interaction point to reduce the background. Another feature of the background is that it is asynchronous with respect to the bunch crossing. So in principle, sensors that can measure the position, the energy, but also the time can help to reject part of it. What I want to communicate to you here in this slide is that the problem is complicated and full simulation studies are mandatory to study the muon collider experiment reaches. So in this study, we studied the production of single Higgs at a muon collider, and the goal is to determine the sensitivity to the cross-section measurement and to the determination of the coupling of the Higgs with the big quarks. Here, for example, you can see this event. This display at 1.5 TeV of collision energy, where you have the Higgs, you can see the 2 jets in the calorimeter, plus the beam-induced background. And you can see this high combinatorial of tracks produced by the beam-induced background. So we studied this process with a full simulation, and we used for this study the detector developed by the MAP collaboration that was not optimized for the full event reconstruction. In fact, for the jet reconstruction, we applied a rough jet reconstruction algorithm, where the background is subtracted on a statistical basis from the calorimeter cells. Then a cone algorithm is used for the clustering, and a jet energy correction is applied. As you can see here, you can see the construction efficiency as a function of the PT of the jet, and the jet resolution as a function of the PT. We have efficiencies around 60–70% and resolutions around 30%. So these performances are not optimal, but they are decent to demonstrate that we can do X physics with a muon collider. We have also a fake rate of 15%. So the tagging to tag the B jets from the X decay are needed. So for the bit jet tagging, we implemented with this algorithm where secondary vertices are reconstructed using tracks inside the jet cone. Here you can see a couple of observables related to these secondary vertices. In red, the distribution for the signal, X to BB bar, and in black, the distribution for the background. This is the lifetime, and on the right, the secondary vertex mass. And you can see that the combinatorial and the signal they have different distributions. So cuts can be applied on these observables to remove the fake tags from the combinatorial. We are able to tag B-jets with a 60% efficiency and with a misidentification between 1 and 3%. So putting all these efficiencies together, here, for example, you can see the jet invariant mass of the X at 1.5 TeV in the center of mass. But this study has been done at 1.5 TeV because we have the background available generated for this center of mass energy, but we extrapolated also to the 3 TeV and 10 TeV case. Using a conservative approach, basically we used the same efficiencies obtained at 1.5 TeV, but the background is expected to be lower at higher energies, so this is very conservative. Then we assumed the forced mass years of data taking at the luminosities expected by the muon accelerator program. And we determined the cross-section as in a counting experiment, let's say. For the coupling sensitivity, we used this formula. You need not only the cross-section of the X to BB bar to measure the coupling with the B quarks, but you need also the X width and the coupling with the W, where we took the uncertainty on the X width and the coupling with the W from the click expectation, since we expect to perform similar to click. So we consider also the physics backgrounds, mainly due to the electroweak processes. And in this table, you can see the three cases at the three center of mass energies and the sensitivity that we expect on the cross-section measurement and on the coupling. So for example, 3 TeV, we have an uncertainty of 0.6% on the cross-section and of 1% on the coupling. These values are compatible with those expected by click at 3 TeV. But you have to consider, as I told you before, that here very conservative assumptions have been done. So our next study is a preliminary. It is a study of the double X production, where the 2X decay in B quarks in B jets. So for this study that we are doing at 3 TeV, we use the modified version of the click detector with the nozzles and with the different vertex detector, and also there are some differences also on the tracking system. And if you want to see details on this detector, you can check the talk by Massimo on the last Wednesday. And we are using the LC-soft framework for the full simulation reconstruction. The signal backgrounds are generated with Wizard, and you can see this feature of the X produced in these collisions. The X in the double X is likely to be emitted in the forward region. And this is true at 3 TeV, but it is also more forward at 10 TeV. So we compared the distribution for the signals with the background. The background is the 4B's background, that it is male dominated by ZZ and X plus BB bar events. Here you can see, for example, the jet mass of the X with the highest transverse momentum on the left, and the jet mass of the second X in the event. You can see in the background that there are two peaks, one near the Z mass and one near the X mass. In this case, to reconstruct the algorithm, we are using a more advanced algorithm based on the particle flow. We select events with at least 4 jets with the transverse moment greater than 20 GeV. So in addition to the X masses, also the angular observables can be used to separate the signal from the background, as you can see in this plot here, where we have the maximum angle between the jets. So as a first attempt to estimate the double X cross-section uncertainty at 3 TeV, we applied the tagging efficiencies obtained in the 1.5 TeV case. Again, we are doing this because we have the background generated just at this center of mass energy, and again, this is very conservative. We are using a 5 observable boosted decision tree that has been trained to separate the signal from the background. You can see, for example, the distributions of the background in blue and for the signal in red here. And with 4 years of data taking, we expect to collect at 3 TeV 1.3 inverse Aptobarn, and we expect to select 67 double X events and 700 background events. So with a fit
so we have
simple
2 more
fit to
minutes.
BDT, you can see the result of this fit.
We have 2 more minutes.
Almost at the end. You can see this simple fit to the BDT, where the X signal is in red, the background in blue. You can see the expected data points. And we extracted an uncertainty on the cross-section of 33%. So I am at the conclusions. In principle, the muon collider is a dream machine for the X physics. It is very challenging, both from the accelerator point of view, from the detector point of view, but it may allow the measurement of the X potential and the couplings with an excellent precision. So full simulation studies are needed to determine the muon collider physics reach. This is due to the beam-induced background. It is very complicated. It is something that is very different from what we have seen till now, for example, in the hadron colliders or in the positron electron colliders. So we have to develop detectors optimized to deal with this background. We demonstrated that with a 3 TeV muon collider, we can measure in 4 years the X coupling to the big quarks with a precision comparable to click, around 1%. The studies on the measurement of the double X cross-section are ongoing, and with these conservative assumptions, we can already obtain good results. But this is just the beginning, because there are a lot of rooms for detector improvements, so we expect to reduce these uncertainties that we are quoting here in this talk. And this is my last slide. Thanks a lot for your attention. And now I'm available for the questions.
Okay, great. Yeah, thank you very much for the presentation, Lorenzo. And if you have any question or comment, please use the raise hand feature of the Zoom. Okay, Michael, please go ahead.
So the B tagging is very essential here. First of all, what is the tracking technology that you're using? Is this all silicon or something else?
So sorry, can you repeat which is the tracking? Sorry.
What is the technology for the tracker here?
For the tracker, we have silicon pixels.
Okay, and
yeah, we have silicon pixels. Yes, please go ahead.
In the vertex detector, what's the occupancy when you include the beam-induced background? Let's just talk about 1.5 TeV. I'm sorry, can you hear me?
I can hear you, and Lorenzo still are there? Maybe we missed him.
Maybe we
Let's
missed it.
wait a little bit.
Oops.
So it seems that, sorry, it's Donatella Lucchesi speaking. I'm a collaborator of Lorenzo. I can answer because
Yes,
it seems
thank
that
you.
Lorenzo, it seems that Lorenzo has been kicked off by the connection. So the occupancy is very high in the when we include is basically dominated by the beam-induced background. So at the moment we have something like 300 or even more. I mean, in the first layer, it's per centimeter square. So is per millimeter square. So it's something very, very high. And we are using. Okay, Lorenzo, you are back. So I was trying to answer because I saw you. Okay,
yeah,
so
sorry, I disconnected just in the middle of the question.
Okay. Well,
okay.
But I thought that the 4 quark background is something like 100 times the, let's say, the double Higgs background. So if you have a 4B tag signal, you're completely dominated by mistags. Is that correct, or am I missing something?
Well, if we have a 4 tag, if we tag 4 jets, we expect to not have the, for example, the light quarks or light jets background, the mistag background in principle, because we have a mistag of 1%, but again, this is very conservative, so we believe that we can do much better. But with our estimation, we have that the mistag backgrounds is quite negligible with respect to the 4B's background. By the way, the 4B's background is 110 times the double Higgs background.
Mm-hmm.
It's not easy to disentangle these two contributions, by the way.
Okay. So yeah, thank you very much for the discussion. Now we need to move to the next presentation. So thank you very much for the presentation and also the discussion. And the next speaker is the Del Motu from CMS, and the research for additional Higgs boson with the CMS detector will be presented.
Okay, can you hear me?
Yes, I can hear you and see the display and the presentation mode. Yes, perfect.
Okay, excellent. Okay, so thank you very much for this opportunity to present the latest searches for additional Higgs bosons with the CMS detector. So as you know, the boson that was discovered at 125 GeV is so far consistent with the standard model Higgs. However, we also know that extended Higgs sector is strongly motivated. So there are many beyond standard model theories that predict extended Higgs sectors. In particular, one type of extension is the 2 Higgs doublet model. And with this, it typically give rise to 2 CP even neutral Higgses, a CP odd neutral Higgs, and 2 charged Higgses. And there are 2 important free parameters in these 2 Higgs doublet models, and that's alpha and tan beta. So that's the mixing angles and the ratio of the vacuum expectation values of the doublets. And there are different formulations of the 2 Higgs doublet models. So one in particular that's important, that's incorporated in the MSSM is the type 2 Higgs doublet model, where you have up-type quarks coupling to one doublet and down-type quarks and leptons coupling to another. So it's typical then to assume that the lightest CP even neutral Higgs of the 2 Higgs doublet model is that which we've measured at 125 GeV. In this case, then you would expect 2 additional neutral Higgs bosons, one CP even and one CP odd, and 2 additional charged Higgs bosons. So I will report on the latest searches for these types of additional Higgs bosons at CMS, and the analyses reported here use 35.9 inverse femtobarns of 2016 data. Okay, so the first result is a low mass search for charged Higgs decaying to a charm and a strange quark. So this is the dominant charged Higgs decay at low tan beta, and we performed this search in TT bar decays. So one top decays to a bottom and a W, which decays leptonically, and the other top decays to a bottom and a Higgs. Okay, so for this final state, we require a lepton, missing ET, and at least 4 jets where 2 should be B-tagged. Okay, so then we perform a kinematic fit with all these reconstructed objects using the top mass constraint. And the final discriminant then is the invariant mass of the 2 jets that are not B-tagged. So these correspond to the charged Higgs, the invariant mass of the charged Higgs. And we perform categorization based on the charm tagging then of these 2 jets. And here's an example of the invariant mass of the dijet system in the tight charm tagged category. So the main background is from TT bar production, of course, as you would expect, and this is estimated from simulation. So the data agrees well with the standard model predictions, unfortunately. So we set upper limits on the branching fraction of a top decaying to a charged Higgs and a bottom quark from 80 to 160 GeV. Okay, so then the next result is a search for a heavy charged Higgs decaying to a top and a bottom quark in the all-hadronic final state. So there are 2 production processes considered. So the S channel and top plus bottom associated production, where you can see the Feynman diagram here. We target boosted and resolved topologies. So boosted is where either a W or top decays such that you can reconstruct it with a single merged jet. And the categorization then is based on the number of jets, whether you have a boosted top or a boosted W candidate in the event, and also on B-tagging of these jets. The main discriminants used are HT, which is the sum of the PT of the jets in the event. This is used in the boosted category, and the invariant mass of the top and bottom quark that are assigned to the charged Higgs decay. So this is basically the invariant mass of the charged Higgs, and this is used in the resolved category. So these are shown HT for a particular category on the left and MTB on the right. So one of the main backgrounds here is some QCD multi-jet background, and we have data-driven estimates using control regions to estimate these. And also the next main background is from TT bar, and this is estimated from simulation. So again, the data is consistent with the standard model predictions. So we set limits on the production cross-section times branching fraction for a charged Higgs decay to a top and a bottom. So this is shown here, this limit for associated production with the top and a bottom quark. And you can see there are 2 overlapping limits, and these are from the resolved and the boosted analysis, where the overlap is at about 0.9 TeV. We also set limits then in MSSM benchmark scenarios. So this is the excluded area in the tan beta charged Higgs mass plane for the MSSM MH125 scenario. Okay, and then the next result is a search for a heavy Higgs decaying to a Z and a pseudoscalar, where the pseudoscalar is lighter than the heavy Higgs. Okay, so this is the largest branching fraction in the 2 Higgs doublet model when cos beta minus alpha goes to 0. And this is interesting because this is the so-called alignment limit, where the lightest CP even Higgs becomes standard model-like. Okay, so this is the Feynman diagram for this process on the left. And the main discriminants are the invariant mass of the dijet system, where the 2 jets are B-tagged, and this corresponds to the mass of the pseudoscalar, and the invariant mass of the 2 leptons and the 2 jet system, which corresponds to the mass of the heavy CP even neutral Higgs. So then you can see what this looks like for a particular signal. So we've plotted MLLJ versus MJJ for a particular signal in simulation. And you can see that it's appropriate to define an elliptical signal region in this plane. And actually what we do is define 6 elliptical bins around the center of the distribution with this parameter rho, where rho corresponds to about 1 sigma of the signal resolution. So in effect, what we do is go from this 2D distribution in MLLJJ and MJJ to this 1D distribution in rho, where the signal you can see is concentrated at low values of rho, which is essentially the center of the elliptical region. And this is the distribution we use then to perform the final statistical analysis. So the main backgrounds are from Dralian, which is taken from simulation, and TT-bar production, which we estimated using a data-driven approach with an electron muon control region. So, okay, so the data is consistent with the standard model predictions. So we set limits for a particular type 2 Higgs doublet model benchmark, where we set tan beta equal to 1.5 and cos beta minus alpha to a small value, 0.01. So, okay, so these are the exclusion limits then in the MH-MA phase space. So this region here on the top left corresponds to the case where the Higgs, the CP even Higgs, has a higher mass than the pseudoscalar. But okay, you can switch the custodial symmetry and flip this mass hierarchy, and then we're also sensitive to the case where the pseudoscalar has a higher mass than the CP even Higgs. And in this case, we can exclude this region here to the bottom right. Okay, we also show this limit on the right in the tan beta cos beta minus alpha plane for one particular signal. And also, if you're interested, there's a new result from a very similar final state, but a search for a spin 1 resonance, and this was shown in the talk by Dennis. Okay, so the next result I'd like to show is a search for a heavy Higgs undergoing a lepton flavor violating decay to mu tau or electron tau. Okay, so this is possible in many beyond standard model theories. And we investigate 4 different decay channels where you have a mu tau, and the tau can decay electronically or hadronically, or you have an electron tau and the tau can decay muonically or hadronically. So these scenarios are shown in the Feynman diagrams on the left. The main discriminant in this analysis is the collinear mass, where this is a kind of an estimate of the invariant mass of the Higgs, where you assume that the neutrinos are collinear with the visible tau decay products. We also define 2 specific selections for signals in the low mass region, so let's say below 450 GeV, and signals with high mass, so above 450 GeV. So this collinear mass is shown then for the low mass selection on the left for one particular category, and the high mass selection on the right for one particular category. And one of the most important backgrounds here is from fake leptons, and this is estimated using data using Z plus jets events and data, or same sign lepton tau events and data, depending on the category. So again, unfortunately, the data is consistent with the standard model predictions. So we set limits on the production cross-section to produce the heavy Higgs, and by a branching fraction for a lepton flavor violating decay to mu tau or electron tau. And you can see the transition here at 450 GeV between the 2 different selections, the low mass and the high mass. Okay, so then the final result I'd like to show is the search for heavy Higgs decaying to WW. So we consider 2 production mechanisms, gluon-gluon fusion and BBF production. We consider standard model width for these resonances. So interference effects with the background becomes important, and this is considered. We consider the fully leptonic decay of the WW system and the semi-leptonic decay of the WW system. And within these, for the semi-leptonic or for the fully leptonic channel, we consider same flavor and different flavor dilepton states. So these are the main channels within that analysis. And for the semi-leptonic channel, we consider both resolved and boosted decays of the hadronically decaying W. Okay, the main discriminators then are the reconstructible mass Enrico in the fully leptonic decay. So this is basically an estimate of the Higgs candidate mass using the leptons and the met. And in the semi-leptonic channel, the main discriminant is the invariant mass of the WW system. So these are shown here on the left for one particular category in the fully leptonic channel, and on the right for the one particular category of the semi-leptonic channel. So yeah, speaking about categorization, we categorize events based on tagging BBF-like events and gluon-gluon fusion-like events. So there are a number of categories included. So again, the data is consistent with the standard model predictions. So we set limits on the production cross-section of such a heavy Higgs by branching fraction to WW. In our final analysis, we include a factor FVBF in our signal model. And this is basically the fraction of the signal that's due to VBF production. Okay, and for this limit that I show here, this factor is left floating in the final fit to the data, let's say. We also set limits in a number of MSSM benchmark scenarios. So I show the excluded area here in the tan beta MA plane for the MH125 scenario, benchmark scenario. Okay, so there were many other final states that I didn't have time to go through here, but I list some of the more recent ones here. Where you can see we cover a wide range of final states and possible signals. Also, there are searches for light pseudoscalars in the context of extinctions of 2 Higgs doublet models with additional scalars. And this was covered in the talk by Fengwan Dong. And also there are many resonant di-Higgs searches. And this will be covered in the talk by Alicia, which is in two presentations time, I think. Okay, so just to summarize then, I've presented the latest results using 2016 dataset for searches for additional Higgs bosons at CMS. So we've unfortunately seen no evidence for BSM physics, but we have excluded large areas of the possible parameter space for 2 Higgs doublet models. So an example here is shown for the MH125 scenario in the tan beta MA plane. And these are a number of different analyses, a number of different final states, and you can see that they exclude different regions of the phase space and combined a significant region of the overall possible phase space is excluded. But okay, stay tuned because we have many new results to come with the full Run 2 dataset. So thank you very much for listening.
Okay, thank you very much for the presentation, Delmont. And if you have any question or comment for him, please raise your hand. Okay, then let me ask a question. So about the lepton flavor violating decay search. So you mentioned that we have the different optimization for the high mass and low mass regime. And what parameter is particularly optimized for the different mass regions?
So I believe it is one of the main ones is the PT of the prompt lepton. The angles between the leptons and the tau and the missing ET, I believe.
It's probably due to the different background composition.
Yeah,
I guess. Okay.
Yeah.
Okay, thank you very much.
Okay, thank you.
And yeah, and do you have any more questions or comment for him? Okay, so yeah, thank you very much for your clear and nice presentation. And let's move to the next presentation. Yeah, thanks a lot. The next presentation is given by Janetta about the searches for the additional Higgs boson in the Atlas detector.
Yes, let me share my slides.
Yes, thank you. I still don't see the full screen mode.
Yeah, that always takes a while. Sorry for that.
Okay.
Now you should see that.
Yes.
Okay, very good. So I'm giving now the presentation from the Atlas side for searches for additional Higgs bosons. And you already have heard the introduction from the previous speaker. But so far we see an excellent agreement of all measurements with predictions from the standard model Higgs boson assumptions, like we see from coupling measurements, for example. But still we know that the standard model is not the ultimate theory of nature because we know of serious shortcomings, like that we have no dark matter candidate in the standard model. We have now many extensions of the standard model that predict more than one Higgs boson, like, for example, two Higgs doublet models that predict 5 Higgs bosons with 2 neutral CP even, 1 CP odd, and 2 charged Higgs bosons. And the supersymmetry would be one example for such 2 HDM models. We have now a very comprehensive search programs for additional Higgs bosons, and that includes both indirect searches, which are, for example, precision measurements of standard model Higgs couplings, and which are then reinterpreted in BSM extensions, or also, in fact, direct searches for dark matter, where we then can also make interpretations in models with extended Higgs sectors. But here, in context of this talk, we focus on the direct searches, where we have searches for additional neutral Higgs bosons, where we are looking at all possible decay modes. And specifically in this talk today, we are interested in di-tau final state, in diphoton final state, and in 2 Z bosons. Then we also have searches for charged Higgs bosons, where I present today the decay of positively charged Higgs boson to top and bottom. And then we also have searches for double charged Higgs bosons, where I don't have examples today. In fact, you also find a couple of more details at the relevant posters, so I invite you to look at them. I'm starting here with the search for a heavy Higgs boson with decays to a di-tau final state, which is in fact a final state that can be enhanced with respect to other decay modes in type 2 HDM if we look at large tangents beta values. And here we are considering final states where we have either a leptonically decaying tau and a hadronically decaying tau, or where we have then both taus decaying hadronically, where the identification of the tau going hadronically is done by a boosted decision tree. And we have now here 2 different production modes, as you can see here in these diagrams. On the one hand, we have the gluon fusion mode, and on the other hand, we have then here the mode where we also have associated BJETs. And so we have here 2 different search categories in this search, where we have on the one hand additional BJETs and on the other hand not. And so we have a BTEC and a BVTO category. You see here examples then for the leptonic case, both in the BVTO category and in the BTEC category. In both the cases, we have then a reconstruction of the di-tau mass via the total transverse mass variable that you find here, which is the main discriminating variable. And after that, we are, depending on the category, left with dominant backgrounds like top, anti-top, pair production, W plus shed, and multi-shed, which are then estimated via data-driven methods. In this search, we have no significant excess in data with respect to the background expectations, and so various interpretations are done. Like you see here now, for example, in the gluon fusion mode or in the B-associated production mode, and then we also have different variants of 2HDM and the MH125 benchmark model, like you can see here on the right-hand side. And here you see, for example, that then tangents beta values above 21 are excluded if we look at the mass of 1.5 TeV in the MA mass. Then I also present a search for a charged Higgs boson going to top and bottom, and such a charged Higgs boson is predicted in many BSM scenarios. And in particular, in the alignment limit, it can be a dominant decay mode of the charged Higgs boson going to top-bottom if you're looking then at masses above 200 GeV for the charged Higgs boson. Here we are looking at a charged Higgs boson produced in association with top and bottom quarks in final states with an electron or a muon. And consequently, given that this final state is very rich in BJETs, we have then here different categories, which are all jet rich and all BJET rich. And so we require at least 5 jets plus 3 or at least 4 B jets or at least 6 jets plus 3 or at least 4 B jets. It turns then out that the top related backgrounds are really not well modeled by simulation, and therefore rather complicated reweighting procedures done based on the shed multiplicity and the HT distributions, where you also find details in the backup if you're interested in that. And after this reweighting procedure, a neural network is trained on parameters that are related to the shed system, B-shed system. There is quite some list of variables that are going into that, including the different masses of the charged Higgs bosons. And you see here in this plot here for one example mass and the output of this neural network. We have then here no significant excess above the standard model expectation scenes. And so you can proceed with setting upper limits, as you can see here in this plot. And those range then from 3.6 picobarn for low masses to 0.035 picobarn for high masses. And then there are also different interpretations done in the various benchmark models, where you see an example here where then the exclusion is located at low tangent beta values and at high tangent beta values. And you also see the improvement with respect to the previous iteration using the partial data set. I would like to proceed with presenting a search for high mass resonance that is decaying to photon pairs. And here we are interested in resonances above 160 GeV. If we are using here now the invariant mass of the photon pair, then we get an excellent resolution, as you are very well aware of similar searches. And so we can consider here both spin 0 and spin 2 possibilities and narrow and large width assumptions in the case of spin 0. For the case of spin 2, we are then interested in looking at Randall-Sundrum graviton models. In contrast to previous iterations, there is now a common event selection done for both of the spin assumptions, and we also have improvements in the photon reconstruction and identification procedure, so that there's quite some improvement in this analysis. And you see here for the narrow width assumption, some example in the diphoton invariant mass and how that is looking like with the smoothly falling background, and then some example signals overlaid. And both the background and the signal shapes are modeled by functional forms, where a double-sided crucible ball function is used for the narrow width assumption and convoluted with a relativistic Bright-Wigner function for the large width assumption. The background is then taken with functional forms from templates that are built from simulation for the diphoton events and from data control regions for the one photon plus shed events. You can already notice that you have here quite some fluctuations. And in fact, the largest deviation would be 3.29 sigma if we look locally. But if we calculate a global significance, it is just 1.3 sigma. And the mass of that fluctuation corresponds to 684 GeV. This you also can see here in this plot on how this translates here, the fluctuations in the local significances. You can then place upper limits for the narrow width assumption, for example, and you see that this then ranges from 12.5 femtobarn to 0.3 femtobarn for higher masses. Then finally, I present you a search for resonances in ZZ, which then can go either to 4 leptons or to 2 leptons and 2 neutrinos. And here we again have both the spin 0 case and the spin 2 graviton case, and look at mass ranges between 200 GeV and 2 TeV. The combination of both the 4 lepton final state and the 2 lepton final state gives us the benefit that we profit from the mass resolution in the 4 lepton case and from the larger branching ratio in the 2 lepton case. For the 4 lepton case, we require now 2 opposite sign lepton pairs. And there's in fact a very long list of improvements that I can't give here completely with respect to previous iterations. But for example, we have now an improved lepton reconstruction and isolation. We also use p-flow jets. There's an improved event selection. And there's of course also the luminosity increase, just to name a few. We have then background to signal separation by a sequence of recurrent networks and multi-layer perceptrons. And this then results in one classifier for the gluon-gluon fusion category and one for the vector boson fusion category. And depending on the score of the sequence and on the lepton flavor, we then end up with 5 categories. And you see here one example of such an output for the vector boson fusion case here in the top plot. And after this classification in the different categories, we look at the invariant mass of the 4-lepton system, as you can see here in the bottom plot, and can then proceed with this. The main background in this is then ZZ, which is modeled by empirical functions, and the normalization is allowed to vary freely in the fit. Going on to the 2-lepton and 2-neutrino case, here we have then the requirement of 2 close opposite sign same flavor leptons, and obviously given the presence of the 2 neutrinos, we can't reconstruct the full mass fully as in the case of the 4-lepton. Therefore, a transverse mass variable is used, as you can see here, and this analysis is in fact cut-based and relies mainly on missing transverse momentum variable, where a high value in the missing transverse momentum is required, and also in the missing transverse momentum significance. And also given the topology we are interested in, the missing transverse momentum should be in opposite direction to the lepton. The nominal backgrounds are then, as you can also see in the plots here, for the vector boson fusion and for the gluon-gluon fusion case, ZZ and W plus Z, where the W plus Z is estimated with the help of a free lepton control region. And the ZZ comes from simulation with also the normalization allowed to vary freely in the fit. We are then combining both of the channels, and no significant excess is seen here. And then we have different interpretations, which are sophisticated in this case. If we are looking at the narrow width approximation assumption, then we have the fits for the gluon-gluon fusion and for the vector boson fusion processes done separately. That means that the respective other process is then profiled, and that is done to not assume a priori a certain fraction of the respective other process. And in the large width approximation case, we need to worry about the interference effects between the heavy and the light Higgs, and between the Higgs to the gluon-gluon to ZZ case, and this is all considered and included. Then after this, we can make different interpretations. And for example, I show you now the interpretation in the narrow width approximation case for the gluon-gluon fusion or for the vector boson fusion case, but there are also other interpretations available in 2HDM models and also for the Randall syndrome graviton case. So finally, I show you here our summary plot that you probably know. It's unfortunately not yet fully up to date, but what you see very nicely is the updated di-tau result, which really dominates the large tangent beta value. And so to conclude, I presented you now selected searches for additional heavy charged Higgs bosons, where I explained a little bit that there are quite some sophisticated techniques in use, like the hadronic tau identification via boosted decision trees, then also to correct for mismodeling of the top background and jet multiplicity and jet HT based reweighting. There are quite some improved object reconstruction helping and gaining additional sensitivity. We have functional forms to model backgrounds, and there are different variants and sequences of deep neural networks to better discriminate the signal from backgrounds. Unfortunately, we have no significant access in data seen yet, but there are still a couple of searches with the full data set outstanding. But from the searches that I have presented today, you already see that there is a significant update of the constraints in the two HDM models. Thank you.
Okay, Janet, thank you very much for the nice presentation. And yeah, if anybody have a question, comment, please raise your hand. Okay, Maria, please go ahead.
Hi. Okay, so thank you so much for the talk. I was wondering if you could say something more on the mismodeling of the top of the GTR. What if you know which variables are mismodeled, which Monte Carlo are you comparing to, and if you could comment a little bit more on how this reweighting procedure is used.
Yeah, so it's in principle the shed PT related variables and also the shed multiplicity related variables, as you can see here. And that is, so the simulation is with PowerPVR. So that which is the standard of what is used in Atlas. And you see here essentially the slopes. So you can pair shed multiplicity, pair shed PT or HT, correct for these kind of slopes. And you see that in fact here, what happens if you do so, because and then you go here from the top, from the unweighted distributions where you see here the slopes, for example, are showing up in the leading shed PT, to the reweighted case where you are essentially using the functions that you have derived here from these cases and see that then things get flat.
So in these plots, can you, the ones that say reweighted, so sorry, just to make sure that I understand them, the ones that say reweighted still have significant data Monte Carlo agreement. So you mean that this is flat, that is a normalization? So you see, I am looking, for example, at the 6Jets4B and wondering whether this the discrepancy that you see in the first beams, is this something that is not due to this, is how it does relate to the reweighting?
Yeah, so in this step, you're really interested in the slopes that you see initially here in the top. I mean, this is, as you can see, still pre-fit. So all of the analysis do some final fit that then include all the backgrounds together and the signal in the end, yeah, to then really obtain the results and the interpretations in particular. But the point is with this top related backgrounds that this analysis correct before even putting into the fit, and there you are then really interested in the slopes, so in the shape differences that you see in these distributions that you want to correct in that step.
If I may, how do you handle the systematic uncertainties? What do you do for which kind of systematic uncertainty do you apply to this correction?
I'm not sure in that case what exactly uncertainty is made on the reweighting procedure itself. Of course, all the analysis include all the uncertainties from the theoretical calculations as well as the experimental uncertainties, where in this particular case, in particular, the shed energy scale and resolutions are relevant for these kind of discrepancies.
Maybe we can take advantage of Mattermost for the following up that.
Thank you so much.
Okay. Yeah, thank you very much for the discussion or presentations. Then, yeah, let's move to the last presentation of the part. Yeah, the next speaker is Lesier, and the title is "The Search for the Resonant Higgs Production at CMS."
Hi, can you hear me and see my slides?
Yes, I can see you and yeah, see the slide in the screen mode. Okay, go ahead.
Hi everyone. Today I will talk about searches for resonant di-Higgs production with the CMS detector. So I will briefly give an introduction about di-Higgs. So right now we are all focusing our efforts on looking for physics beyond the standard model. And it is well known that the Higgs sector is an important portal to new physics. And then in the Higgs sector, the di-Higgs production is a mechanism which is of very special interest. And now I will briefly discuss why this is the case, so why it is so important and how it manifests itself, so how somehow we can detect it. So the di-Higgs production cross-section at 13 TeV and at the LHC is about 33 femtobarn at next to leading order in QCD. And this cross-section is too small to be observed. However, there are some BSM models that predict an enhancement of this cross-section. And this new physics can appear basically in two ways. So the first way is the non-resonant di-Higgs production or anomalous couplings of the Higgs. So this means that when the di-Higgs is produced in a non-resonant way, and this you can see in the top row diagram, and this is the standard model-like production. This is a golden channel to study the Higgs potential because, as you can see here, these diagrams can probe the Higgs trilinear coupling lambda and also the top Yukawa. However, there are also some BSM effects that can be added to the Lagrangian through dimension 6 operators. And this you can see in the bottom row diagrams, where you can see now that these diagrams are, well, they are dependent on these Wilson coefficients and also the trilinear coupling. The second way is the resonant production. That means new particles that decay to a Higgs pair. So this you can see in this diagram here. So you see the production of a new resonance X that then decays to a pair of Higgses that are standard model-like. Now this process is predicted by many BSM models. And one of them is the Randall-Sandrum warped extra dimension, where we have that predicts the presence of a scalar, so spin 0 radion, or a spin 2 graviton. And then we have Higgs singlet model and 2 Higgs doublet model and MSSM. And a large mass range for the resonance X is being probed. So right now we go from 250 GeV, which is twice the mass of the Higgs, to currently 3 TeV. And then an important remark that I want to make here is that if the mass of the resonance is too large to be observed, then we cannot see the resonant production directly, but instead we can detect it by looking at anomalous couplings of the Higgs. This talk is entirely focused on resonant di-Higgs searches, and instead for the non-resonant, see Ivan's talk, which is right after mine and the coffee break. So in the di-Higgs searches, we have a large variety of final states possible. As you can see here in this plot, depending on how both Higgses decay. So the decay channels are chosen based on the branching ratio and the purity, and the main ones are listed here. So we have the 4B's final state, meaning that both Higgses decay to a BB pair. And this has the highest branching ratio of all, but also very high QCD and TT bar contamination. Then we also have the BBWW, which has also a very high branching ratio, but also it suffers from a largely reducible TT bar background. And then we have the BB tau tau, which has a medium branching ratio, 7%, and a relatively low background. And then the BB ZZ and BB gamma gamma, which are the channels with the lowest branching ratio. The gamma gamma is even 0.3%, it's very low. But also there is a low background level for these searches. Now in the next slides, I will present recent results on di-Higgs searches on the 2016 dataset. So the first search is the di-Higgs to 4Bs. Now this topology is dependent on the mass range probed. So if we stay at low masses of the resonance mx, then the two BB pairs can be resolved. But if we go higher in mass, up to 2 TeV, then we can treat one pair as resolved and one as merged. And then if we go further higher in mass, then the Higgs pairs, the BB pairs cannot be resolved anymore because the 2 Higgses are very boosted, are very energetic. So we will treat the BB pairs as two fully merged jets. So let's start from the resolved search. So in this case, two main kinematic regions are defined. We have a low mass region and a medium mass region going up to 1.2 TeV, so an intermediate mass. Events are selected with 4 jets, of which at least 3 must be tagged. And here ability is used for B-jet energy regression that improves the sensitivity of the analysis. And the main background is multi-jet QCD, which is modeled from data by doing parametric fits in the sideband regions. And you can see the results on the right in these 2 plots. So you see model independent limits, and then you have the interpretation assuming the presence of a graviton on the top and assuming the presence of a radion on the bottom. You can see, especially for the radion, that basically it can be excluded over almost the whole mass range probed here. Okay, moving on to the semi-resolved and fully merged searches. So these 2 searches are very similar. In the semi-resolved search, 1 B-tagged fed jet is required together with 2 B-tagged jets. And 2 categories are defined here according to the separation in eta between the 2 jet structures. So low delta eta is more signal-like. And instead, in the fully merged, we have 2 B-tagged fed jets and central jets are selected. And 2 categories here are defined according to the double B-tagger value. In both searches, the discriminating variable is the reduced Higgs invariant mass, and you can see a plot here for both searches. And the main backgrounds are multi-jet, which is data-driven, and TT-bar plus jets. And these are the results. So here the results from the 2 searches are combined. And one interesting thing to notice is that below 2 TeV, we have an improvement in the sensitivity of the analysis when we treat one pair as resolved and the other one as merged with respect to the fully merged analysis. When we go above 2 TeV for the graviton interpretation and 1.6 for the radion, then there is no sensitivity gained from the semi-resolved analysis, and instead the fully merged analysis only is used. Moving on to the BB tau tau search. So here events are selected with 1 isolated hadronic tau and a second lepton of opposite charge, which is an electron or a muon or an hadronic tau. And events here are categorized according to the number of p-jets. And the main backgrounds are TT-bar and Relian, which are taken from simulation, and multi-jet, which is taken from data. And ability here is used to discriminate against the main background, which is TT-bar. And the search is a search for an excess in the invariant mass distribution of the Higgs, which is taken from a kinematic fit. Here you can see the results, again, the model independent limits on the left, and this is also interpreted assuming a radion with this particular benchmark. And here all the channels are combined. And instead on the right, you can see the interpretation in the HMSSM. So here among the 3 parameters of the theory, you have 2, which are the mass of the A and the tan beta. And here, we can exclude basically the region for MA in the 230 and 360 GeV range, and tan beta up to 2. Now these are searches where 1 Higgs always decays to BB and the other Higgs decays to a pair of vector bosons. So it can be either a Z or a W. So in this particular search, the vector bosons can be either WW or ZZ, but in any case, the final set is always the same. It's always 2 leptons and 2 neutrinos. So here, 2 isolated and opposite sign leptons are required together with 2 beta jets. And the categorization is done according to the lepton flavors and the invariant mass of the dijet. And the backgrounds are TT bar, which is estimated from simulation, and Drelian, which is estimated from data. And here the main feature of this analysis is a parametric DNN to scan over a fine range of MX. And the final discriminant of this search is the output of the DNN. And again, here you can see the results. So you can see the model independent limits, again interpreted in the case of a bulk graviton on the left and radion on the right. The next search is always H decaying to pair of vector bosons, but in this case, these vector bosons are two Ws, one decaying hadronically and the other one decaying leptonically. So the B quark pair from the Higgs, from one of the Higgses, is reconstructed as a single jet. And then the one isolated lepton is required, and this lepton must be nearby a jet of the merged W2QQ decay products. And the main background here is TT bar, which is suppressed by reconstructing the di-Higgs decay chain and applying mass constraints. And the maximum likelihood fit is performed on the 2D distribution of the invariant mass of the two Bs and the invariant mass of the di-Higgs. Again, here you can see the results, the model independent limits, and again, the interpretation for a graviton and a radion. And here you can see that the radion can be excluded up to more or less 1.2 TeV. Another search where in this case the vector bosons are ZZ. Here one of the two Zs always decays leptonically, and the other one can decay either to a pair of quarks or to a pair of neutrinos. Now this is the first search where the Z decays hadronically, and it's also the most recent result in CMS regarding the resonant Higgs. The main backgrounds here are Drelian plus jets and TT bar, and we also have the multi-jet background in the case of hadronic decay of the Z. So in the case where the Z decays hadronically, the final state will be BBLLQQ. And here the jets are assigned to the Z and to the H according to the Bitak discriminant and the H mass constraint. And a BDT is used here to discriminate against the multi-jet background. And the search for an excess is performed in the BDT discriminant distribution. In the case where the Z decays to neutrinos, the final state is BBLL nu. Here there is a cut on the invariant mass of the two leptons to be above 76 GeV, which is to reduce the contribution from the BBWW search. And the search is done in the HH transverse mass distribution, and you can see a plot here on the bottom.
We have 2 more minutes.
Yes, thank you. These are the results where the two channels are combined. So we have the BBLLQQ and the BBLL nu. And also here, it's important to notice that the interpretation was also done in the exotic Higgs, in this case, the N2HDM, and it's the first time that this is done for this search. The last search that I'm presenting is the BB gamma gamma. So here events are selected with 2 identified photons and 2 B jets, and the categorization is done according to the BDT discriminant and the HH reduced mass. And the signal extraction is done in 2D from a parametric fit of the invariant mass of the dijet and the M gamma gamma. And the main background here is the non-resonant background, the gamma gamma plus jets, which is data-driven, estimated from the sidebands. And here you can see the results again on the right for different for 2 different benchmarks for both radion and graviton. Now I just want to highlight that for some of the searches that I presented, a combination was performed, and specifically on the 4B's search on the BBLL nu, BB tau tau, and BB gamma gamma, and here you can see a plot with the combined limit. So to conclude, the resonant Higgs production is fundamental in the search for new physics. The BSM models predict an enhancement of the cross-section of this production, and a large variety of final states is investigated, and it's always a trade-off between background and purity, and for this reason it's important to explore and then combine many decay channels. Now the CMS collaboration has delivered excellent results with the 2016 data, and now we are all looking forward to more results from searches on the full run 2 data. And thank you for your attention.
Okay, thank you very much for the nice presentation. And now let's start the discussion. So if you have a question or comment, please raise your hand. Okay, Jason, please go ahead.
Hi, on slide 13, when you're discussing the single lepton BBWW, you mentioned that you require one isolated lepton nearby a merged W2QQ.
Mm-hmm.
Does this mean close but not within the jet cone?
I think so. So the thing is that in this analysis, all the objects are treated as boosted. So you see the BB is reconstructed as a fat jet, and then also the WWDKs must be close to each other. So I think indeed it's close, but not within, yes.
Okay, but so then this would limit how boosted you could actually go.
Exactly.
Okay.
Yes.
Okay, thank you.
Okay, thank you very much for the question and the answers. Does anybody have a further question or comment? Okay, so thank you very much for the presentation again. And now we are starting the coffee break. So still we are running a little bit late. Let's restart the next presentation at 11 a.m. And yeah, also the Zoom room is available during the coffee break. So yeah, the presenters for next sessions, please feel free to test your audio and the sharing the displays during the coffee break. Okay, so yes, thanks again for all the presentations, and let's start the coffee break now. Thanks a lot.
Good afternoon. Can I test my sharing?
Yes, please go ahead.
Okay, thanks. So,
Okay, I can see you.
Good.
I can hear you.
Slides.
And I can see the slides already in full screen. Can you try to cycle them a bit? Just go to, yeah, okay, perfect.
Thanks.
Okay, thanks a lot. And talk to you in 20 minutes.
Okay, thanks.
So can I also test the screen?
Sure, please go ahead.
Okay.
Okay, can you see the slide? Can you try to put them full screen?
Yeah, so I already put it on the full screen.
Okay, perfect. Okay, and if you want, you can, yes, and if you want, you can also try to enable your video for your talk so that people will.
So let me also turn on my video to test it works. Yeah.
Okay, all good.
You can see mine?
Yes.
Okay, great. Thanks.
See you later, or talk to you later. Bye.
Hi, maybe I will also try to share and test my screen.
Yes, please.
Okay, just a sec.
Sure.
Okay, do you see my screen?
Yes, can you try to go full screen?
Yes. Is it okay?
Yes, now it works.
Okay, perfect. So,
And you are also welcome to turn on your video.
yeah, just. Is it okay?
Yes, I can see you.
Okay, perfect.
Hello, Valerio, can I try now?
Yes, Stefan, please go ahead.
Okay. Full screen. Okay.
Okay, I can see clearly the slides full screen.
Yeah, so there is only the issue of the
video.
When I share, maybe I will switch on my video before. Okay, I found it. Okay, so it should be.
Okay, perfect.
Okay, so see you later.
Yes, bye.
Hey Valerio, can I test my setup now?
Sure, Max, go ahead.
Thanks. So first, hi.
Okay, I can certainly see you, hear you.
All right, sharing screen. Gonna share this one.
Okay, try to go full screen. Okay, perfect.
Do you see it?
Yes, all good.
Excellent. Thanks a whole bunch. Stop. And stop. Okay, talk to you soon.
Hello, this is David. Can I test my setup?
Sure, please go ahead.
So let me start video.
So we can see you.
And,
a bit of some reflection.
yeah.
That's okay.
And then share my screen. There you go.
I can see the slide full screen.
Okay, so it works?
Yes.
Okay, fine. Thanks.
Cool. Talk to you later.
Okay, so it's time to restart the session. This is going to be the last part, and it will be mostly dedicated to the Higgs management and production. And clearly, the Higgs is one of the goal for both LSC Run 3 and also iLumi LSC and the future. So Ivan or Ivan?
Yes, I ready.
Okay, we can see you.
Okay, so
okay, please start when ready.
Okay. Good afternoon, everybody. I am Ivan Ovchin from Novosibirsk State University. My talk about search for non-resonance change production at CMS. Few several slides. It is some remember about previous talk. So now about motivation. This list presented famous diagrams at leading code for gluon-gluon fusion HH production. HH production is sensitive to Higgs self-coupling, lambda HHH. This parameter contains information about shape Higgs potential, and the main mode for this production it is gluon-gluon fusion. But we have small production cross-section due to discretive interference between triple coupling and box diagrams presented on the slide. This right presented dependence cross-section from K lambda, where K lambda determined as deviation from value self-coupling for standard model. GluGlu-HH cross-section, it is 31 femtobars. For vector boson fusion, we have cross-section 20 times less. But beyond standard models can significantly increase cross-section and change the final state kinematics. So move to next slide. In effective field theory, gluon-gluon fusion production for HH described by 5 diagrams presented on the slide. First 3 slides diagrams appear in beyond standard models. We have 5 parameters which controlling Higgs level interactions. Each point in this 5D current phase space lead to different kinematics and cross-section with help modification Lagrangian presented on this slide. Last 3 members in this Lagrangian in standard model equal 0. So move to next slides. Points in this parameter phase space can be clustered, leading to similar kinematic distribution on final states. On bottom plot, this left presented an AHH distribution for 12 benchmarks. How we can see, we have now a different distribution from HH in shape, and we have 12 benchmarks. In each cluster, we have same final states and choose only one set of parameters indicated red line. In right table presented chosen parameters for 12 benchmarks. For each benchmark, we extract limit for explore EFT sensitivity. Also, we can reweighting any MC sample to any other from the combination of these 5 parameters. It is needed for scan for kappa lambda. So move to next slide. Now about explored final states. We have now a rich set of final states, which is assignable at the LHC. This left presented the branching for different final states. For example, for BB gamma gamma, we have 0.26% branching. We must compromise between high branching and purity from background for Explorer. First explored final state with 4 budgets, which have largest branching, larger QCD and TT bar contamination. Second final state with 2 budgets and 2 vector bosons, which have larger branching, larger TT bar contamination. The final state with two BGs and two tau leptons, which have sizable branching and relatively small background. More sensitive final states, it is BB gamma gamma, which have small branching but good diphoton mass resolution, sense the electromagnetic calorimeter CMS, and relatively small background. So move to next slide. Now about first final states, which we will consider. For select events, the requirement for identified BJets, then pirate into Higgs boson candidates. BTAC is crucial for this final states and requirement 3 BJets in trigger level. Main background is QCD multijet, and BDT is trained to separate the standard model change signal from background. Background is estimated from data with hemisphere mixing technique. This hemisphere technique presented with right. We divide original events in two hemispheres. Then we have library from such hemispheres, and then we create a new data like it event with same final state. It is a low decrease small signal fraction in original dataset and have good background. Signal extraction performed from BDT output. BDT output presented on left plot for data and mixed data and standard model signal. On this slide, presented results for 2016 year with 35.9 femtabars. Observed upper limit at 95% confined level is 847 femtabars. In standard model prediction times, it is upper limit is 75. Also set a constraint on kappa lambda larger minus 23 and less 30 for BCMs. So move to next final states with two BJs and two vector bosons. Selected events with two opposite charged leptons and two BJs. Events come from two processes with two BJs and two W bosons and two BJs and two Z bosons, and where bosons are decaying into neutrinos and two leptons. Also, we have mass requirements that d-lepton mass larger 12 and less MZ minus 15 GeV to suppress quark-Cornier resonance at Z boson backgrounds. We have larger irreducible background from TT bar and Drell-Yan process, therefore DNN to discriminate signal from background performed. Binet maximum likelihood fit performed to DNN output distribution in 3 different MGJ regions and 3 channels. For example, presented this right DNN output for 3 different MGJ regions for mu plus mu minus channel. This right presented results with 35.9 femtopars. No excess is observed in data, and upper limit observed is 72 femtobars. In standard model prediction times upper limit it is 79. Also set upper limit as a function of ratio kappa lambda to kappa t, which we can see on left plot. Red line it is to standard model prediction theory when kappa t equal 1 and kappa t equal 2. Red line it is observed, upper limit expected is dashed line. So move to next slide. It is second final state with two BJs and two tau leptons. Selected events with one isolated tau leptons decaying hadronically with second lepton opposite charge. Event categorization performed according number of BJs. Main background it is TT bar Drell-Yan process and QCD multijets. BDT performed to discriminate from TT bar background in leptonic channels. more important variables in training, it is transfer mass. It is largest mass of parent particle compatible with kinematic constraints of event. Being at maximum likelihood fit to perform it on transfer mass distribution with 3 final states. This right presented distribution for transfer mass for data, backgrounds, and signal. Presented results for round 2 with 35.9 femtobars from 2016 dataset. Observed upper limit, it is 75.4 femtobars. In standard model prediction, observed upper limit, it is 30. Also set upper limit as a function of ratio kappa lambda to kappa t for BCMs. Kappa result presented on plot with left. Kappa lambda larger minus 18 and less 26 for case when kappa t equal 1. So move to next slide. It is more sensitive channel to standard model ICHEP production BB gamma gamma. We have high BB branching plus excellent d photon mass resolution. Main background, it is non-resonance d photon plus jets and resonance equal Higgs, where dominate the background, it is TT bar. Even categorization performed with scope two variables, MVA and MX. MX determined with scope of this equation presented on this slide. Distribution for MVA and MX presented on right plots for data, backgrounds, and signal. Signal extraction performed through a parametric fit 2D fit of M gamma gamma and MGJ. Distribution for data with fits presented on bottom plots for M gamma gamma and MGJ. On this slide presented results for round 2 with 35.9 femtobars. Observed upper limit, it is 2 femtobars. In standard model predictions times, it is 24. Kappa lambda larger minus 11 and less 17 for BCMs, and correspond plot presented on this slide.
You have 3 minutes left.
Okay, thanks. On this slide, presented combination results for these final states, which we consider. Observed upper limit is 22.2 in standard model prediction times. This right presented constraint on kappa lambda for combined result. Kappa lambda larger minus 11.8 and less 18.8. So move to next slide. And on this slide presented value upper limit for different benchmarks, which we consider on 4 slides. We have now different value upper limit for different benchmarks. Here presented results for final states and combined result. So move to next slide. It is new results. It is first analysis that investigated the HH non-resonant production in BZZ with 4 leptons in final state at LHC. Selected events with 2 pair oppositely charged related leptons and less 2 jets. Main background is single standard model Higgs boson production. Z plus X background estimated from data. BDT output used to discriminate between signal and background, and training performed in signal region where for lepton mass larger 115 GeV and less 135 GeV, plus requirement number jets larger 2 or equal to. BT variables, it is PT of 4 leptons, which is used in training. Delta between 2 Higgs bosons, PT and beta score of 2 selected jets, D-jet invariant mass. We have different trainings for final states. So signal extraction is performed through multidimensional fit to BDT. BDT output presented on right plot for backgrounds and data and signal. So move to next slide. These results for new final states which are investigated. Results for full run 2 with 137 femtobars. With left presented constraint on kappa lambda larger -9 and less 14. With right presented upper limit for 3 different years and combined result it is 30 in times standard model prediction. So it is my last slide summary. CMS searches for default Higgs production presented. We study several final states. Search not yet sensitive to standard model production, but limit from combination and crystal stringent. Various BCM scenarios tested and preliminary CMS results for full run 2 with 137 femtobars for final state with 2 BGS and 2 Z bosons, where Z bosons decaying in 2 leptons channel presented. And full run 2 results for several final stage ongoing. We expect soon new results. Important to combine different channels and experiments. New data will be collected in run 3 and highly university LSC. Thank you.
Thanks a lot, Ivan, for the nice talk and also the first new result on the Higgs production with full run 2. Question or comments from the audience?
Yeah, can I speak?
Yeah, please.
So, imagine that some BSM scenario is realized in the nature. So, are the DNN net or BDT discriminants sensitive to the? So, I mean, did you check that the shape of these discriminants is sensitive or insensitive to the different scenarios? Because you fit only. If I got correctly, you fit the template with the assumption that the standard model is correct, right?
Yes.
But if, for instance, some crazy combination in BSM applies, then would that change the shape of the BDT output?
Yes, the requirement for BDT consider standard model scenario.
But I think on slide 14, you can see the impact of this right on the left-hand plot, because that is exactly the deformation, right? Where you're changing to BSM Higgs self-coupling scenarios, and this actually has a pretty mild dependence, it seems. So I assume from this plot that it's not that large of a change.
Okay, thank you. Mm-hmm.
Okay, Catherine?
So mine was actually a request. Do you have a link to your pass note or like your note for this BBZZ result?
Sorry, I bet here question.
I was just wondering if you had a link to the note for this.
Link, yes.
Maybe you could post it on the Mattermost.
Oh, okay.
Thanks.
So
Okay, one quick
maybe
one from Maria. Yeah, sorry. Or it's a
yes,
follow-up.
it's just to follow up. So the public note is going to go out this morning. Okay.
Perfect. I couldn't
We
find
waited
it.
for the talk to release it, so it will go out this morning in the usual place for CMS notes.
Okay, thank you.
I still think that if you have time to just post it on the Mattermost chat when it's public, people will probably appreciate it. Okay, we can now move to the next talk, which is from Atlas. So, David?
Yes, hello. Can you hear me?
Yes.
Okay, let me quickly start the video and share my screen. there we go.
Okay,
Can you see it?
Yes, you can start already.
All right, so yeah, it's my pleasure to present the latest results and searches for Higgs production in ATLAS, both non-resonant and resonant searches. So yeah, we already heard some words of motivation in the previous two talks, but yeah, I want to just quickly give you my perspective on why it is important to look into the Higgs production. So first, the Higgs final states give access to multiple physics phenomena, and most notably the standard model. You all know this famous Lagrangian equation of the standard model, where by now many of its terms are actually well tested, although the actual core of the electroweak symmetry breaking, the potential of the Higgs field, is not measured by any experiment yet. This potential includes this term lambda, which parameterizes the trilinear Higgs self-coupling. And yeah, measuring this is very challenging because of the small Higgs cross-section. This comes from, yeah, so there are two contributions, which are shown in the Feynman diagrams on the right, which have a destructive interference. So you have this trilinear Higgs self-coupling, but you also have the non-resonant Higgs production via a top quark loop. And yeah, actually one of the major goals of the high luminosity LHC is to measure this Higgs cross-section and the trilinear Higgs self-coupling, and this will be covered by another talk in this session. So if the lambda or the cross-section is as low as it is predicted in a standard model, we won't be able to measure it with the data recorded so far. However, in run 2, we are already sensitive if the lambda deviates from its standard model prediction, and such anomalous couplings are parameterized with this kappa lambda value, which is basically the coupling strength over its standard model prediction. And changing this value can have a large impact on both the cross-section and the kinematics. So this you can see on the plot on the lower right. There you have, for example, in red, the kappa lambda equals 1. This is the standard model prediction. And if you compare this, for example, with the yellow graph, kappa lambda equals 5, you see that the cross-section is almost an order of magnitude higher. But also the Higgs spectrum is shifted, in this case, to more softer values. And then finally, we are also sensitive to beyond standard model resonances. So there are many beyond standard model scenarios that predict the heavy resonance decaying into two Higgs bosons. So for example, you can have a spin 0 resonance as it is predicted by two Higgs doublet models like in the MSSM, or in electroweak singlet models, or you can have a spin 2 Klein-Kaluza graviton as it is predicted in a Rundle syndrome model of warped extra dimensions. So after we know why we want to find the Higgs production, let's talk about how to actually do this. So the Higgs further decays, so you end up with a variety of final states that you can look into. Here on the left, on the table, I've listed the branching ratios of the most common combinations. And outlined in red are those channels which are covered by ATLAS so far. So you see that most of the channels include at least one Higgs boson decaying into a BB. This gives a high branching ratio, but you can also have leptonic final states which would benefit from high background suppression. And yeah, as if those multiple final states aren't enough, you can further split this, for example, into production modes. So the main production modes for Higgs production is gluon-gluon fusion. But in ATLAS, we also recently started to look into vector boson fusion. And you can also split this depending on the topology of the decay products. So you can have resolved final states, which is mainly important for low resonant masses or for the non-resonant Higgs production. But as soon as you go to very high resonant masses, you will end up with boosted final states. That means that the decay products are so narrow that the usual reconstruction techniques would not work anymore. So in the table on the next slide, here is a list of references with all the publications from Atlas with DieHiggs publications in Run 2. The ones highlighted in red are the most recent publications that utilize the full Run 2 dataset. I will cover them later. Before I do that, I want to come to the early Run 2 results, which have been combined in a DieHiggs combination. So this is shown in the following slides. So here, 6 different channels were combined using a luminosity of up to 36 inverse femtobarn. And here on the plot on the left, you see the upper limit on the gluon-gluon fusion cross-section normalized to the standard model value. And I will cover the most sensitive channels in the following. First, we have the BB tau tau final state, where we look for 2 B-tagged jets and 2 tau leptons, while the tau leptons can decay either both hadronically, or one decays hadronically and the other decays into lighter leptons. There are 4 different triggers considered, with 1 or 2 online hadronic tau decays, or with a lepton or a lepton plus a online hadronic tau decay. In this analysis, a boosted decision tree is used as the final discriminant. And you can see in the plot on the lower right that this boosted decision tree gives a very well separation between the DieHiggs signal for different kappa lambda values and the expected backgrounds. So then we have the 4B final state, which consists actually of 2 different analyses. So first we have the resolved analysis, which is mainly used for the non-resonant DieHiggs production search and for low resonance masses. Here we search for 4 jets, which are B-tagged. And then we also have the boosted analysis, which is mainly sensitive to high resonant masses. There we look for 2 large radius jets, and each of them must include 1 or 2 B-tagged track jets. And then finally, the invariant DieHiggs mass is used as a final discriminant. And then here, this is the BB gamma gamma final state. There we look for 1 or 2 B-tagged jets and 2 high PT isolated photons. And then we have different jet PT selections depending on if we look for non-resonant or resonant production. And as a final discriminant, the gamma gamma mass is used, as you can see in the plot in the middle. And then I also wanted to note that although the BB gamma gamma has the smallest branching ratio, this can be largely compensated by the fact that it has a very high acceptance times efficiency. At least if you compare it to the BB tau tau or the 4B analysis, you see that the acceptance times efficiency is almost an order of magnitude higher. This comes, for example, from the lower thresholds of photon triggers. And also, due to the high background suppression, this analysis was able to even include a 1 B-tag region, which gives further improvement in terms of acceptance times efficiency. So then coming to the combination. So with all 6 channels combined, we see that the gluon-gluon fusion cross-section could be constrained to 6.9 times the standard model prediction. And the kappa lambda is constrained to between -5 and +12. And the plot on the upper right, you see the exclusion limits as a function of kappa lambda, and in red, the theory prediction. Then, as I said, we are also sensitive to beyond standard model heavy resonances. And here we have set limits on the production of a narrow scalar resonance and the spin 2 Kaluza-Klein graviton. The cross-section limits can be seen on the plot on the plots on the left. And there you also see that the BB gamma gamma is most sensitive at low masses, At intermediate masses, it's kind of a mixture between BB gamma gamma, 4B, and BB tau tau. And then at the highest masses, the boosted 4B analysis is most sensitive. We also set limits in the parameter space of the HMSSM. This is shown on the lower right. There you see that we are mostly sensitive or can exclude low tangent beta values. And we have also set limits in the parameter space of electroweak singlet models. I have more on this in the backup in case you're interested. So then coming to the latest results that utilize the full run-2 data set. So here in the DiHiggs to 4B final state, we had a first look into DiHiggs production via vector boson fusion. Vector boson fusion gives you those 4 different Feynman diagrams here on the top. And it also gives you a very distinct event topology with 4 central BTEC jets and 2 high PT forward jets. As you can see in the plot on the right, the multi-jet background is the most dominant background. And here it is estimated from data by using events with a lower B-jet multiplicity. And then this is also validated in Higgs mass sideband regions. So the vector boson fusion cross-section is even lower than the gluon-gluon fusion. So this is just a bit more than 1 femtobarn. So that then finally the observed limits on the VBF cross-section is 840 times the standard model. But what is even more interesting in this channel is that one has a direct access to this quartic coupling, which is highlighted in red in the Feynman diagram. There you have a coupling between 2 vector bosons and 2 Higgs bosons. And this can, again, be parameterized in a kappa framework in this kappa 2V value. And here it is constrained to between minus 0.76 and 2.9. And here on the lower right, you see the exclusion limit as a function of kappa 2B.
You have 3 minutes left.
All right, thanks. Then with the BBLL final state, we have a first search for standard model DiHiggs production via gluon-gluon fusion with the full run-2 data set. Here, 1 Higgs decays into BB and the other Higgs decays into 2 vector bosons or 2 taus, which then further decay into 2 light leptons plus neutrinos. So naturally, we select then for 2 BTEC jets and 2 electrons or muon with opposite sign, with opposite electric charge. And for the final signal region, a deep neural network classifier, the MLL and the MBB cuts are used. This deep neural network was trained on DiHiggs signal and also on the 3 most dominant background categories, which is from top, Z2LL, and Z2 tau tau. And then finally, an observed limit on the gluon-gluon fusion DiHiggs cross-section was set to 40 times the standard model. And on the right-hand side, you can see the distribution of this neural network classifier. And then we also have the boosted BB tau tau final state, which extends the existing resolved BB tau tau analysis to higher masses above 1 TeV. Here, a novel technique to reconstruct boosted tau pairs is employed for the first time in an ATLAS search. On a plot on the upper right, you can see that the di-tau reconstruction in black is much more performant than the resolved tau reconstruction in red when you have very low distances between 2 taus. In this reconstruction, a pair of 2 hadronic tau decays is reconstructed as a large radius jet, which has at least 2 small radius subjets. And then finally, a boosted decision tree is applied to reject the large background of quark or gluon-initiated jets. And a plot on the lower right, you see that, for example, at the signal efficiency of 60%, you have a background rejection of 10,000. That means that only 1 out of 10,000 quark gluon jets is misidentified as a boosted di-tau. And then for the BB tau signal region, we reconstruct the Higgs to BB candidate as a large radius jet, which has then track jets inside for the B tagging. You see in the upper right the signal region. So finally, this is a cut and count analysis with a very small expected background, mainly coming from boosted Z to tau events. And then finally, we are setting limits on the production cross-section of a heavy, narrow scalar resonance, as you can see on the lower right, with masses between 1 and 3 TeV. So then coming to the summary. So I hope I could convince you that di-Higgs signatures are key for better understanding the electroweak symmetry breaking. By now, the strongest constraint on the di-Higgs production are still set by the early run 2 combination, where we had upper limits on the cross-section at 6.9 times the standard model and kappa lambda constraint between -5 and 12. And yeah, we can look forward to see this updated with the full run 2 data sets, potentially discovering new physics or further constraining standard model couplings. In the meantime, new channels are also explored, like the vector boson fusion in a Higgs 2,4b final state, or new final states like BBLL or the boosted BB tau analysis. Thanks for listening.
So thanks a lot, David. Time for questions. Okay, I will start with one. Oh, okay, Maria, thanks.
Well, I mean, I have a very simple one. So if you go to the, well, or very general one, how much does this boosted BB tau new result, that is actually very nice to see, improve upon the previous limits on the resonant Higgs? Can you compare to the other channel?
Yeah, one can say that still the boosted 4B analysis is most sensitive. So this comes mainly from the improved branching ratio that we have in the 4B analysis. And yeah, as you can see, so the BB tau has the advantage that it potentially can suppress background and in particular multi-jet background better. But as you can see in the plot here on the upper right, we are really looking for just a couple of events. And yeah, if you go to the highest masses, then this additional branching ratio gives you a large improvement.
Okay, thank you.
Thanks. More question? I think I have a maybe quick one, although admittedly I should know. On the VBF, the Higgs, could you maybe comment on how many assumptions are you making on the other couplings? Like, are they all set to standard model? All the other, let's say, possible diagrams?
Yes, I think so. I mean, I would need to double check in the paper, but I think they are all set to the standard model expectations.
Okay, thanks. Okay, I think that, well, this question was also a bridge to next talk. If there are no more comments or questions, we can go to Max.
Can you see me?
Yes, we can hear you, we can see you.
All right, and then the last step is, can you see my screen? And can you see the full screen?
Not yet full screen. Okay, yeah, now it is. So please start when ready.
Excellent. Okay, well, thanks everybody. I'm very happy today to talk to you about measuring the Higgs self-coupling with die and single Higgs processes, which is a fun sort of unique analysis done by the Atlas collaboration. So everyone has in the session so far given their personal take on why the self-coupling is important. So it's time for my turn. So we know from our measurements so far to LHC, the Higgs is really at the center of the standard model. The process, and what I mean by this, it's not just in this diagram, of course, but the process of electroweak symmetry breaking is what creates the massive gauge bosons. The Higgs field is what gives masses to all the fermions. And so really you can say that the standard model doesn't make sense without the Higgs. So understanding the Higgs is key to understanding the standard model and potentially physics beyond. Now, what's one thing that we don't actually understand very well about the Higgs so far is actually its potential. So in a standard model, we have something that we write down, which is this. This is sort of the simplest thing you could write down. It looks like this, and it has a minimum. This minimum is where we live because the Higgs field rolls into this lower energy state. The initial symmetry broken. The field acquires a non-zero vacuum expectation value. And this is the Higgs mechanism that you know and love. But many other shapes could have caused the same physics, something squished and wider like this, or many other potential shapes as well. So we don't actually know the shape right now. We haven't measured that. We just know some of its properties, namely that there is a minimum that we live in. So why does this matter? Why do we want to measure the potential? Well, the answer is that many models alter the Higgs potential. So for example, models of electroweak baryogenesis have the Higgs potential undergo a phase transition in the early universe. And that could explain matter-antimatter asymmetry. And this sort of plot here shows the Higgs potential in these kinds of models as a function of the temperature or at various temperatures. Now, this phase transition actually requires modifications to the standard model potential. You can't have this process of electroweak baryogenesis with the simple standard model Higgs potential. So you need something else. And generically, it turns out it's actually hard to modify only the potential and not change other Higgs couplings. So this is something we'll get back to later, which will be an important part of this talk. So basically, this means if we can measure the shape of the potential, we can find hints of fundamental critical new physics that tells us about the early universe and why the universe is the way it is today with matter-antimatter asymmetry and things like this. So how do you measure the potential? Well, we know that at least in the standard model, it looks like this. It has this minimum. If you expand around the minimum, expand around where we live, you just try to get a local view of what the universe in our corner of it sort of looks like, or our potential part of the potential, what it looks like. You get these kinds of terms. You might recognize this term. This is the mass. This is obviously well measured. There's a lot of analyses that do a very good job of measuring that. Now, this additional term is the Higgs self-coupling. So you can see just from doing this math out that the standard model itself is predicting di-Higgs production. And in particular, diagrams like this on the right are what you would potentially get from the standard model if you were looking for di-Higgs production. You have this triple coupling of the Higgs boson, which we often call the self-coupling, and will get you from the standard model, no BSM required, di-Higgs final states. And you'll have a coupling, which is this, as predicted by a standard model. But you can also think about this in a slightly different way, is that this is a Taylor expansion, and we want to measure this third term. We just want to sort of go further out in a Taylor expansion and understand what's out further. And so you can think of this higher order term as telling us more about the shape of the potential. It could have the standard model value, or it could have some other value. And we often call this other value kappa lambda. We just parameterize that by normalizing by the standard model value. So it's just a multiplicative factor on the standard model value of this coupling. Now, in this measuring this with di-Higgs, we already heard from David and Ivan about this. We have this kind of diagram that produces two Higgs bosons. This coupling is what we want to measure, and this is what tells us about the shape of the Higgs potential. The tricky thing, of course, is that this process on the right also has the same final state, but kappa lambda doesn't appear. So there's no information about the Higgs potential in this diagram on the right. Now, these two diagrams have different numbers of fermions in their loops, which means they actually are going to interfere destructively when you take their sum. And so that leads to the very low cross-section that we've heard the other speakers talk about. What's also important about this, though, is that kappa lambda sort of here, especially on this diagram on the left, is intrinsically tied to kappa t as well. That means our sensitivity to kappa lambda can change if you also allow kappa t to float. So this coupling of the Higgs boson to the top quark, which is what actually produces the initial Higgs boson in these final states. So how do you measure these processes in di-Higgs? We've heard a bit about this already, but the critical observation is that if kappa lambda isn't a standard model value, then interference sort of diminishes and you get larger cross sections. So on the right, you can just see as a function of kappa lambda what the cross section looks like. And you can see that there's dramatic orders of magnitude increases as the kappa lambda changes.
But while the cross-section can increase, as David pointed out, it's the lowest MHH component that is most enhanced. So, and this plot on the right, which I took from the Dye-Higgs white paper, which is a nice resource you can read there, you can see that this triangle diagram, which is the thing that tells you about the self-coupling, that's what's enhanced as you enhance kappa lambda. But this is obviously also the lowest energy, lowest sort of MHH area. And so it's difficult to extract information when you're just enhancing the sort of highest background area as well, the signal in the highest background area. So this means that measuring kappa lambda is challenging, and you need both rate and shape information for the best constraints. So as David showed, this is sort of the current Atlas Dye-Higgs result at kappa lambda. So you have in the orange the cross-section that we showed previously, and then in the colored lines, color dashed and solid lines, you have the three most powerful Atlas analyses, and the black is the combination of these. And so you can see that there's this dip in the middle. This dip is caused by, essentially, it's easier to observe things when the kappa lambda is low in some sense, or near standard model, because you're more dominated by the box diagram, which has higher MHH contributions. And as you enhance kappa lambda, you get a higher cross-section, but the signal becomes more difficult to observe. So obviously these Dye-Higgs searches set strong constraints on kappa lambda, but this is assuming the only new physics is in kappa lambda. And as we mentioned earlier, it's hard to sort of generically come up with a model that has only new physics in kappa lambda. So can we say anything else? And the answer is yes, we have other measurements that are potentially sensitive, and those are measurements with single Higgs. So it turns out that single Higgs final states can also be sensitive to kappa lambda. And you can see the sort of diagrams that contribute here. Critically, these are all next to leading order electroweak corrections to the Higgs cross-section, to the branching ratios, and to the kinematics. If you sort of do all the calculations out, you can see that, for example, on the right, this is how as a function of kappa lambda, how the various single and Dye-Higgs cross-sections change with kappa lambda. It's a very mild dependence, for example, on the GGF. You can see in the blue in this upper right plot how it does change very subtly with kappa lambda, but our precision, obviously, on the GGF cross-section is extremely good right now, so you can still make interesting statements from just this kind of cross-section. Similarly, at the bottom right, you can see how the branching ratios change as a function of kappa lambda. And this is also very important because our precision on the branching ratios is improving all the time as we collect more data and the single Higgs measurements really become quite precise. So how do we combine the single and double Higgs measurements? So we do this combined analysis using these list of searches. I'm not going to go through the details of any of these. David already talked about the Dye-Higgs searches earlier today. And on previous days, I believe Matt and others have spoken about the sort of single Higgs analyses at the top. I did put links here so you can check out the details of any of the individual analyses you're curious about. In terms of how we use the information from a single Higgs analyses, we just use the cross-section for the GGF production modes and the TTH production modes. And then we use STXX template fits for the VBF and VH, because the kinematic information that's accessible via the STXX gives you a little bit of additional information for those production modes. There's explicit analysis overlap checks done to check how overlapping the single and Dye-Higgs searches are. It turns out the only significant overlap is in the TTH to gamma gamma, which overlaps very much with BB gamma gamma. And so the TTH to gamma gamma result is neglected. So then we provide two kinds of interpretations. One where we do new physics only in kappa lambda, which is sort of similar to what's been shown before. And then new physics with kappa assumptions reduced. So what does this look like when we look at just kappa lambda? So on the left here, we have what's just the log likelihood on the y-axis and the kappa lambda on the x-axis. This is the expected of the combination. You could see that the double Higgs results that we might have, we saw similarly from David's slides are in the black. Single Higgs are in the blue. What's nice is you can see these are sort of same order of magnitude. They're competitive, which is nice to see. And that means that the combination is even narrower in this likelihood plot. And so you can read off sort of what the exclusion range is where the 95% confidence line intersects with the red line here from the combination. The observed, of course, is slightly different, but you can see once again that the red combination is stronger than any of the individual searches. So this is really nice to see already from just the kappa lambda that the single and Dye-Higgs are providing similar limits. I should note, of course, that the single Higgs in many cases has 2 times the luminosity of the di-Higgs searches. So especially the diphoton and ZZ searches, I believe, are updated to 80 in femtobarns here. So they're quite a bit more just statistical power than the di-Higgs searches. So this will change once everything is at the same level. But you can see there is complementary power, and the combination provides the strongest limits. Now we can talk about relaxing constraints. So this plot is a little bit complicated, but let me walk you through it. On the x-axis, we have kappa lambda as usual. On the y-axis now, we have kappa t. So kappa t, as we talked about in the di-Higgs measurements, is sort of intrinsically tied to the analysis because you're always measuring kappa t and kappa lambda together because you're producing via gluon-gluon fusion always. So you can see in the black lines how if you sort of allow kappa t to float, the di-Higgs measurements actually lose quite a bit of sensitivity. And they can't constrain kappa t at all, obviously. Now, once you put the single Higgs in, so the single Higgs, because has measurements with VBF, VH, TTH, and so on, is actually able to constrain kappa t independently from kappa lambda. And then you put those all together, and you really get the best combination overall with the red. So this means that this is just an example of how the single Higgs can provide complementary information to the di-Higgs searches and sort of enable the best possible extraction of limits when you allow more generic kinds of BSM models.
You have 3 minutes left. Sorry.
Great, thank you. Nearly done. Then we can also talk about sort of models with even fewer constraints. So in this plot, for example, we show once again a kappa lambda on the x-axis, the log likelihood on the y-axis. In the red is the kappa lambda only model, which we have sort of shown before, but we can also just let all the other kappas, kappa W, kappa Z, kappa T, kappa B, kappa lepton, let all of those float. And when you do those, you can obviously see that the constraint is sort of a little bit weakened compared to a sort of more stringent theoretical assumption. There's more degrees of freedom in the fit, so you get weaker constraints on sort of our parameter of interests. But we do know that new physics could affect couplings beyond just kappa lambda. And so it's important to consider these most general constraints. And that's very difficult to do without single Higgs. The di-Higgs searches alone wouldn't be able to make this kind of statement very clear. So what can we do next? This paper showed a sort of a nice view of what can happen at the LHC, HL-LHC. The prospects for measuring, this is again the sort of likelihood on the y-axis, although here it's a chi-squared. On the x-axis, it's kappa lambda. And in the red, you can see sort of what the prospects are for measuring the kappa lambda via HH processes. And then adding the single Higgs and differential information in single Higgs can help constrain the kappa lambda a lot. And the combinations obviously are even better. So this is sort of an input to the European strategy paper strategy update. So it shows that really these single and di-Higgs processes together can help us reduce assumptions and even expand to EFT models with even fewer constraints than the kappa framework that we've been talking about previously. So wrapping up, Atlas has performed a unique new measurement combining single and di-Higgs final states to measure the Higgs self-coupling. With more physics constraints, we can relax the model assumptions and test more realistic deviations from the standard model. The combination provides not only the most precise, but also the most general constraints on the Higgs self-coupling. So thank you very much. Happy to take any questions.
Thanks a lot, Max. And also to perfectly stick to, or actually gaining probably 1 minute on the schedule. So question time. Okay, maybe I will start so that people will feel more happy to ask later. Clearly, you pointed nicely that the measurements currently are complementary, but well, the Higgs combination or the single Higgs results contains much higher luminosity, right? So
Yes.
do you have a feeling of how your comparison might look at the end of the, let's say, run 2 with the whole analysis scale to, well, the full luminosity?
Yeah, that's a good question. I think I'm trying to go back to the plot that had the first comparison. Yeah, from this you can see that the double Higgs is still a little better on the left than the single Higgs, and this is even with the 2x luminosity for the gamma gamma and ZZ channels. So it's probably going to be that it's still a little bit more dominated by di-Higgs when we're looking at these kappa lambda only models. I think that the single Higgs, though, is always going to provide extremely important information with the more general models. And there, as we saw with this sort of 2D plots like this, di-Higgs alone is always going to struggle here. So I think that the story is going to be for kappa lambda alone. If you really want to make that assumption, then di-Higgs will be more dominant. But then as we start exploring more general models, single Higgs will always be contributing important statements.
Okay, thanks. So more chance for questions. Okay, doesn't seem to be the case, but just remember that there's always Mattermost, and I see that it's getting interesting active with the question also from the previous subsection. So thanks a lot, Max, and then we go to the prospects, starting with CMS. So Sandhya, I apologize if I misspelled.
Yeah, I'm here.
Okay, we can see the slide. Can you put them full screen?
Yes. Just a sec. Okay, there is something. Okay, so,
perfect. The start one ready.
Yeah, sure. Okay, so today I'm going to talk about the Higgs boson measurements and di-Higgs production at the high luminosity LHC with the CMS detector. So what we have learned so far at the LHC experiments is that the theory of standard model is robust with the discovery of the Higgs boson, and unfortunately, there is no direct evidence of new physics at LHC so far, which means there are still open questions that remain unanswered. I won't go into detail here, but answers to these questions may lie at the TeV scale, providing us a strong motivation to look for the new physics. Now, what can the high lumi LHC do for us? It basically provides access to the new particles indirectly, where one can look for deviations from standard model expectations, indirect loop contributions, and very rare processes. And this figure shows you the LHC and the high luminosity roadmap in the coming years. And you can see by the end of high lumi LHC, we are expecting to have about 3 Autobahn inverse of data, which is about 20 times the sample that we have. And this will be done at, this will be provided at 14 TeV center of mass energy. And with this much amount of data, one can perform the precise study of standard model like Higgs properties that we will discuss in the coming slides. So just a word before moving on the challenges and the detector upgrades. Because of the high luminosity that we are foreseeing, of course, the pileup and the radiation dose increases, which initiates the need of the absolute detector upgrades. And to meet the machine performance, CMS has major phase 2 upgrades planned, including the new NCAP calorimeter and the new tracker, new readout for the barrel calorimeters, and so on. So coming back to the expected physics potential at the high luminosity LHC in the Higgs sector. Now, we have had a lot of talks so far. We know that Higgs physics is a major component of high luminosity LHC physics program. In itself, Higgs, it will be a Higgs factory where we expect to produce more than 150 million Higgs boson, which are distributed over its main production mechanisms, which I've shown in the Feynman diagrams here, and the bar chart here, which shows it will have, each production mechanism will definitely have more than 1 million Higgs produced. So which enables essentially Higgs precision measurements of couplings, cross sections, and so on. And we will definitely have the di-Higgs production where we will have about 100K events, which enables the Higgs probing of the Higgs self-coupling. And of course, one can study the sensitivity to the rear decays and couplings and beyond standard model Higgs direct searches at high Lumi LHC. So now coming to the analysis approaches at high Lumi LHC, there are various analysis approaches that have been used to access the sensitivity in searching for new physics at high Lumi LHC, including full simulation, fast simulation, and projections. So for full simulation, one uses the most updated phase 2 geometry, algorithms, and tunings with the PILAB simulation. In fast simulation, one uses the parameterized detector performance using Delphis. And for the projections, existing signal and background samples have been used from the 13 TV analysis to higher Lumi and corrected, and they have been extrapolated to higher luminosity and the corrected efficiencies. And for the uncertainties, there are two scenarios which have been used, which is run 2, where which is referred to as S1 in the coming plots, and where no change in the systematics is done, and they are propagated as it is what we have in run 2. And then for the S2 scenario, which is the yellow reported lean scenario, where theoretical uncertainties are reduced by a factor of 2 compared to what we have now, and experimental ones go as 1 by square root of integrated luminosity until they hit the detector capabilities. So coming to the probing of the Higgs production and decay rate, signal strength, cross-section, and the coupling measurements, before going to the results on these, I would like to state 2 caveats. These are the projections which are performed from results which were obtained with the 2015 and 2016 data sets corresponding to 36 femtobarn inverse of data, which means this is just order 1% of what is expected at high Lumi LHC. And thus these projections are very limited to what we expect from the real analysis at high Lumi LHC. So now coming to the results, here this plot on the leftmost plot essentially shows the, oops, sorry, just a sec. Okay, so this plot on the leftmost shows the expected 1 sigma uncertainty per production mode. And here in green, we have the S1 scenario, the uncertainties corresponding to S1 scenario. And in red, we have S2. And in blue, we have the statistical ones. So for the production mode uncertainties in S1, the main component of uncertainty comes from the signal theory, except the WH mode, which is essentially statistically limited. And while in S2 scenario, it is, signal theory remains the main contribution, while VBF production mode is also statistically limited. For the expected 1 sigma uncertainties per decay mode, here overall, the signal theory uncertainty is the largest component for all, except the case for mu mu analysis, where we have the analysis is statistically limited, and however, this analysis critically depends on the dimuon mass resolution, which is expected to improve by 40% in the new tracker that we will have for phase 2. So overall, in the uncertainties for per production mode, we expect to reach 3 to 6% of uncertainties per production mode, and for per decay mode, we expect to reach uncertainties of about 3 to 5%, except of course for mu in the S2 scenario. And then for the Higgs cross-section and the branching fraction measurement, here in this plot, it shows the combined measurement of ATLAS and CMS for combined for the expected uncertainties on cross-section per production mode. And in blue here corresponds to the statistical, and green is the experimental, and red is the theory, and the gray is what we have as the total uncertainty. So one can see here that for GGH and VBF, contribution from statistical, experimental, and theory are almost similar. However, for WH and for ZH, it's mainly the statistical and the theory uncertainties. And while for TTH, theory uncertainty is really a factor of 2 larger compared to the other ones. Then overall, the uncertainties range from 1 to 6%. For the uncertainties on the branching fraction measurement per decay mode, the main component is the signal theory uncertainty, as you can see for all except mu mu and the z gamma, which are again statistically limited, and overall the uncertainty range from 2 to 4%. So now coming to the coupling modifiers, we know that these are introduced to parameterize deviations from the standard model Higgs boson couplings to standard model bosons and fermions. And depending on the process or the decay mode, these are defined like this. And what this plot shows is the CMS projection, assuming the branching friction to of the Higgs to the BSM final state fixed to 0, the uncertainties on for all the decay modes here, and the combined one on the right for ATLAS and CMS. So what we can see here is that uncertainty components for kappa gamma, kappa W, kappa Z, and kappa tau, they contribute at the similar level. However, for kappa tau, kappa G, kappa top and kappa G and kappa B, the statistical ones, the theory ones are the main ones, while these one for kappa mu and kappa Z gamma remain statistically limited. Overall, here also we have, do you still see my full screen?
You're a bit scrolling the slides, but I think it's still decent, unless people strongly object.
Just, okay, so.
Okay, now it's much better.
Okay, so.
Thank you.
No problem, thank you. So then, yeah, so overall here also we expect a precision of 1 to 4%. So now coming to the differential Higgs cross-section measurement, here we know that the differential cross-sections measurement is important because it allows to look for the tails, and they are very sensitive to the they are very sensitive in the high PT region. And what is shown here is the PT distribution of the Higgs, and for 3 different decay modes combined for Higgs to BB, Higgs to gamma gamma, and Higgs to ZZ. And here we can see that the uncertainties in the higher PT region are actually about a factor of 10 smaller compared to run 2, where whereas in the lower PT region, they are no longer statistically dominated, but the reduction in the systematic uncertainties in the S2 scenario yield a reduction of the total uncertainty up to 25% compared to S1. And the table here shows essentially the values of these uncertainties at 3000 femtobarn inverse for each bin to be able to have a look at the numbers itself. So now coming to the Higgs pair production and self-coupling, again, before moving on to the results, this analysis has been done with the Delphis using the parameterized simulation software and pile-up simulation of 200 pile-up events, and this has been explored.
2 minutes left. Sorry.
Sorry. So this has been explored in 5 different decay channels. As we know that Higgs mostly decays to BB bar, along with BB bar, but other Higgs is allowed to decay to BB, tau tau, WW, gamma gamma, and ZZ. And the results for di-Higgs production is shown here, where the scan of the expected likelihood is shown as a function of kappa lambda here in all the 5 channels that I discussed before, and the combined one in black. What is important to note here is that kappa lambda measurement has been obtained with a significance of 2.6 sigma. And at 68% confidence level, and a signal strength of 0.77 has been obtained with 95% confidence level. And the results on the combinations from ATLAS and CMS will be shown in the next talk by Stefan. So quickly coming to the sensitivity to the beyond standard model effects in Higgs physics. There are several studies that has been explored specifically for Higgs to invisible decay mode. We see that the 95% confidence upper limit has been shown as a function of minimum threshold on the missing transverse energy, and one can explore up to the 95% confidence limit on the branching fraction to be less than about 3.8%, which is here, compared to what is shown for run 2 of about 24%. And there are again other BSM scenarios which have been explored where the limits on the branching fraction have been shown to be less than 6% from the coupling combinations compared to what we have from run 2. I have linked the papers where from you can compare these numbers. And then there was a specific study which was also done for the anomalous couplings and the Higgs width measurement, where significant improvements were shown. And there was one specific study which was done to also study the BSM Higgs signatures by using the L1 trigger information, L1 track information at so that one can trigger on these signatures, which are actually really the blind spot for analysis at the current moment. And then there was enhanced improvement which was shown with HLLHC for additional Higgs boson searches and scalar searches. For example, in the MSSM Higgs to tau tau search and the scalar Higgs mass search with this scalar going to ZZ and to 2L2Q channel. So to summarize, Higgs to High-Lumi LHC, it's essentially a first Higgs factory which provides potential for precision measurements and new physics discoveries in the Higgs channel, in the Higgs sector. And we see that the most Higgs cross sections and couplings are can be performed at a few percent level precision. However, many measurements are limited by the systematic uncertainties, so we need a lot of work from both experimental and theoretical side. For the di-Higgs coupling, we have a significance of 2.6 sigma. And this will be shown that with the combination of Atlas and CMS, one can reach a significance of 4 sigma in the next talk. And it was also shown the sensitivity to BSM physics can be enhanced, and the Higgs physics, Higgs width can be measured within 1 MeV. So there are exciting times ahead. So I will just end my discussion here, maybe.
Okay, thanks a lot.
Thank you.
So for this huge amount of expected result, let's say, time for questions.
May I ask you one quick question?
Yes, please.
Yeah.
Thank you very much. About the expectation for the precision of kappa parameters. So to estimate that all the other kappa parameters is fixed to 1 or all of them are floating?
I think it is fixed to 1 as far as I know. Maybe someone from the group can correct me if I'm wrong.
Sorry, I missed the question. Can you repeat it?
Yeah, the question is, so in estimation of the precision of kappa parameters, the all the other kappa parameter is fixed to 1 or also floating?
So I understand. This is the typical combined fit for all the like the one shown yesterday. So it is it's done in combination. It is not fixing and it's and then looking at and one. It is really a combined fit of all the decay modes. I think that is what Shandia has said already. Sorry.
Okay.
Okay, thanks.
Thanks. So more questions? Doesn't seem to be the case, so I propose we go to the equivalent talk from Atlas, and maybe after that people will have more questions on the possible comparison of the two results. So Stefan?
Yes, can you hear me?
Yes, we can hear you, we can see you.
Okay, so now I will share my screen.
Full screen.
Okay.
Perfect. You can start already.
Okay, so after this nice presentation from Sandhya for the CMS prospects, it's my pleasure to present the similar results for the Atlas collaboration on the Higgs and the di-Higgs. So the outline of my talk will be, so the first slide will be about the high luminosity LHC description, so machine and detector upgrade with a strong overlap with Sandhya, so I will be able to be quick. And then for this presentation, I decided to focus only on the standard model Higgs physics program, starting with a single Higgs production and what you can get out. And I will have one slide on the H to CC bar, a presentation on the differential cross-section, the Higgs boson coupling to fermion boson. And then for the last part, I will go through the non-resonant di-Higgs production with a potential first observation of the di-Higgs production at HLLHC and the measurement of the Higgs boson self-coupling. And I will finish with the next step for this program. So the top picture, you have already seen it with a full LHC program. So if you look on the right, you see the high luminosity one. Important dates, so between 2025 and 2027, we have the upgrade of the detector on the machine, and then we start for a 10-year program. And this high luminosity LHC can be presented as a thing we can get the most with LHC infrastructure. So this is the maximum integrated luminosity we could achieve in a decade. And the plan is to provide an integrated luminosity of 3000 inverse femtobarn, which would correspond to a gain of factor 9 compared to run 3. On the physics program, so this was already elaborated. So it's a physics beyond the standard model and also understanding the electroweak symmetry breaking. And so Higgs properties is one of the main items, and it's a portal to understand the fundamental basis of standard model. What will be presented today corresponds to the last global update campaign, which was published for the CERN Yellow report last year. And I finish by one caveat. So I will speak about 3000 inverse femtobarn, But you can see on the picture that there is still potential increase to 4,000, which would increase the luminosity by 33%. At HLLAC, we will have new operation conditions for detector, which will be more tough. So we will have to sustain an increased instantaneous luminosity by a factor 2 to 4 compared to round 3, which means a higher pile-up, which would reach a number of interaction per bunch crossing of with a mean value of 200, and at the end, a larger integrated radiation dose. But on the other side, we want to maximize the physics outcome per inverse femtobarn. So we will maintain or improve the object construction efficiency and resolution. And we plan to reduce the fake rates even with a more pile-up jet. So what are the solutions to reach these objectives? So these are solutions which are described in the technical design reports which were published over the last year. So upgrade the electronic readout with new technologies, replace the detectors with the most recent technologies in general. And for example, we will have a new inner tracker. Extend the angular coverage to the forward region. This is done through the high granularity timing detector, which will be a new detector, and the new inner tracker. And the last but important thing is that we will improve our trigger and data acquisition system in order to be able to sustain a higher rate, but also to extend its capabilities. For the CERN yellow report, the analysis strategy could not be the same as for run 2 because we didn't have a fully simulated Monte Carlo. So what was done was to do some extrapolation from the latest published LHC analysis results. So what is presented here is based on what I call early run 2 data, which correspond to the 2 or 3 first years of run 2, which correspond to 36 of or 80 inverse femtobarn. And then you scale the statistical uncertainty, assuming 3,000 inverse femtobarn, and of course you reduce by a factor which is the square root of the ratio of integrated luminosity. For HLLAC, we plan to increase center of mass energy to 14 TeV. So for the extrapolation, the signal on the background cross sections were increased to this energy, which roughly means an increase by 10 or 20%. And the default assumption on object construction performances and fake rates was that thanks to the upgraded detector performances, we will be able to compensate the degradation induced by pileup. There is a second approach, which was used only for the double Higgs to BB gamma gamma study, which is to use the parameterized performances of upgraded detector layout. And in this case, we produce particles at generator level, and we smear them according to the expected efficiencies, resolution, and fake rate. Last point on introduction, so it's about systematic uncertainty. So we have large event statistics, so systematic will become critical. So for the CERN yellow report, there was a joint ATLAS and CMS effort to agree on common systematics. On the theoretical part, the agreement was to have a reduction by a factor 2, except for PDF, energy scale values, and for the background TT plus heavy flavor. On the experimental side, we have scaled down the systematic to the floor value. And one last point, which is in the result, you will see the impact of the limited number of simulated events was not included, but you can find the estimation of this impact in the documents, in the ATLAS documents. So to summarize the scenario for the systematic, or we keep the early run 2 values, it's called S1, as it was already presented by Sandhya, or we have S2 or reduce, which corresponds to the CERN yellow report. Now, one slide about Higgs to CC bar. So this is a low branching ratio, 2.9%. So any new physics could have a significant impact on this branching ratio. So the first attempt was done some years ago through the exclusive decay of Higgs to J psi gamma and the J psi decaying into 2 muons. This analysis was extrapolated from the run 1 The left plot indicates the kind of mu mu gamma invariant mass distribution which we will obtain. So in blue, you have a huge background, and in green, you have the small Higgs signal. But even in these difficult conditions, people expected to be able to put a limit on the branching ratio at 15 times the standard model. But more recently, there was a run-2 analysis, which was done to look for Higgs to CC bar, but looking at associated production. And in this case, we have looked at Z to dileptons. This analysis was extrapolated from the 36 inverse femtoband sample and analysis strategy. The bottom left plot shows a typical distribution in the case where you have selected events with 2 C-tag jets, and the PT of the Z greater than 150 GeV, and in the red line corresponds to enhanced signal. And nowadays, we expect the limit on the branching ratio at 95% confidence level without systematic at 6.3, the standard model. And as you can see from the plot, we have a significant background, so you have to control it. And if we degrade the control we have of the background, we think that it could increase this limit by 36%. For the future, we think that we can enhance the sensitivity just by adding the W to lepton neutrino and the Z to 2 neutrinos channels. Now, Higgs differential cross-section. So this is interesting because when you look at the PT of the Higgs, but also the variables, you can be sensitive to the couplings to the C or the big quark. At high PT, you can be sensitive to the new physics at large scale. So in Atlas, for the Cerniello report, we have just included the diphoton of the di-Z decaying in 4 leptons. And we obtained the best precision for the diphoton. This was extrapolated from the 18 inverse femtoband sample, and you can see the results on the right plot, which is a differential cross-section as function of the PT of the Higgs. In the scenario where we have no systematic, full systematic, which is S1, and scale systematic or reduced systematic. And as a conclusion of this plot, you can see that for the low and medium PT Higgs regime, we have a statistical error typically of 3%, but which would degrade to 5% if we have the early Run-2 systematic, and we can reduce it to 4% with reduced systematic. So it's really interesting to reduce systematic. At the large PT Higgs regime, so in the Atlas case, we have 1 bin between 350 and 1 TeV. We have 8% precision, which is dominated by the statistical uncertainty. So it would be interesting to combine with CMS. So the next step would be to do the same exercise, but with the Higgs to BB bar through the VH channel. Now I go to the Higgs coupling to boson and fermions. So we have extrapolated for all the channels which were studied at Run-2. For the systematic uncertainty, so we had the same scenario, but one thing which was interesting in this exercise is that it was the first time that the experts in the computation of systematics had to deal with so low values. So it was a kind of useful exercise for them. The bottom plots are just an example of typical ranking of systematics. So on the bottom left one is VH with H2 diphotons. So the main systematic is related to the diphoton uncertainty on isolation and ID. And on the, we have also the uncertainty on the QCD scale for the signal VH. The right table just gives you a list of numbers for different production mode with the numbers from the Run-2, then extrapolation with HL, LHC scenario 1 and scenario 2. And this is the cross-section for Higgs to gamma-gamma. So you see nicely the reduction on the total systematics, on the total error with the component statistical, which decreases like thanks to the integrated luminosity, and then the experimental and the signal systematics, which decrease less than the integrated luminosity. Summary on the full results. So this was already presented by Sandhya for the CMS and combined part. So branching ratio on the left part, kappa coupling on the right part. So you can see that for almost all channels, we are dominated by systematics, and we have typically uncertainty between 2 and 4%. And now if you look at the dimuon on Z gamma final state, in this case, we have a kappa uncertainty of the order of 10%, 7 to 12%, but which is dominated by the statistics. So
you have 2 minutes.
Okay, so I go to the Higgs now. So, okay, so the production was already presented. So this is challenging because the cross-section is low. But one thing which is also important is that we have at least four particles in the final states. So the selection efficiency is below 10%. We have the largest branching ratio, 4Bs and BB tau tau. They are interesting, but they have a large background. So, okay. And now we have also the low branching ratio with the BB gamma gamma, which is interested. We have a very small background, but in this case, we have few signal events. On the right part, you have the plot, which indicates significance as function of kappa lambda. And you can see that for standard model, we have a typical limit at 3 sigma. And you can immediately also see that it's the BB gamma gamma and BB tau tau channel which contributes the most to this search for the diphoton, for the Higgs. And then you can translate this in kappa lambda, where you see the different distribution. I want to spend 1 minute on the trigger threshold for the Higgs search. This is important for the BB tau tau and 4Bs. For BB tau tau, the background comes from the fake taus, and the plot illustrates the kind of limit you can obtain on the cross-section for the leading and the subleading PT offline threshold. So bottom left part corresponds to current run 2, so you would reach to 0.9. And if you increase a lot this limits, you could reach 1.5, which would be bad. On the right part, it's the same for the Higgs to 4Bs. And the main background is multi-jet event. And you can lose a factor 2 to 4 if you go from 40 to 70 GVPT. The combination, Atlas and CMS. So you have the details of statistical and stat plus systematic for the significance on the left part. And what you can observe is that today we think that we can reach 4 sigma. So we are close to observe the Higgs at HLLHC. On the right part, it's a measurement of the kappa lambda. So combining the two experiments on all channels, we think that we can reach 50% precision on the kappa lambda measurement. And we should be able to exclude kappa lambda equals 0, which means the lack of triple Higgs vertex. Which would be excluded at 95%. So I go to the conclusion, which are the prospects, the next steps. So we have already done these studies for the Senialo report. So the key part for the future is that we have been able to identify the main systematic uncertainties which will limit these measurements. So this gives a roadmap on the theory and the experimental effort. The next update of this kind of results is expected for the SNOMAS review next year in the US. Atlas is targeting critical topics with recent improvements and adding subjects not covered by the Senialo report. And to get this HLLHC program ready in 8 years from now, we still need to optimize the reconstruction of algorithm with the new HLLHC environment and detector layout. And we will benefit from the integration of new algorithms developed for Run 2 and Run 3. So as a conclusion, the HLLHC era will be an exciting period for the Higgs physics studies. Thank you.
Thanks a lot, Stefan. So we open the floor for questions. So maybe I can have a quick one, which is, do you already identify, let's say, beyond let's say the theory uncertainty, which you were pointed out as critical and so on, did you already identify some critical systematics and how they will evolve towards high luminosity. I mean, of course, we can assume that the analysis will be done very differently when we'll have 3,000 inverse femtobar with respect of now.
So one of the things we really hope is that, since, as you say, we will have a lot of data, we should be able to have a better control of the background or experimental systematic through control samples or even some data-driven analysis to control the background. So this is something which is only starting now at Run 2 because we have only few integrated luminosity, but we should really develop all this in the future. And when we cannot do it, we should improve as much as possible the simulation. But as was shown over the last 10 years, we had plenty of new ideas to improve things. So we can be confident that we should be able to reach what we promised today and be optimistic and think that we will do much better than what we promised today.
Thanks. Not mentioning that you should probably find a way to provide also enough Monte Carlo to follow up the data.
Yeah, well, this is also another challenge. It's a production and also storing all this data. But this is something we will learn at Run 3. Run 3 will be a typical, will give the opportunity to study all this and to prepare for Run 4 and 5.
Thanks a lot. So last chance to ask a question also.
Yeah, I have one nice
Thomas.
question. So on page 13, where you compare the significances expected for the HH production for kappa lambda, actually. So the two last channels are only listed for CMS. So I expect the Atlas studies are still ongoing, so we don't have the projections yet. Is that right?
You mean for BBZZ and BB?
Yeah,
exactly. So for this exercise, since Atlas didn't have results, so we assume twice integrated luminosity for CMS. But of course, Atlas will provide them. I'm not sure for SNOMAS, but this should be done.
Okay, and these studies assume the optimistic scenario S2, right?
Yes.
Okay, thank you.
Okay, thanks. So I think it's time to shift from experimental to the theory side. I think the next one is Johannes.
Hi. Can you hear me?
Yes, we can hear you. We can see you now.
Okay, I'm trying to share my screen. Are you able to see my screen?
Not yet, at least not me. If people see it, please speak up. Okay, now it's coming. Something coming up. Okay, so if you can go full screen. Okay, perfect. You can start when ready.
Okay, thanks a lot for the introduction. So first, I'd like to thank the organizer for setting up this conference online and for giving me this opportunity to give a talk. So what I would like to tell you about today are two loop corrections to the Higgs-Triana coupling in models with extended scalar sectors. So this is based on these two papers, and I hope you can see my mouse, together with Shinya Kanemura at Osaka University. So why are we interested in the Higgs-Triana coupling? Well, actually, we heard quite a few reasons already in the previous talks, some nice explanations. But I'd like also now to give you a bit more of maybe a theorist's point of view and at least some reasons why I'm interested in the Higgs-Triana coupling. So the first one is, as also was mentioned, is that since the Higgs discovery, we know that we have a Higgs potential, but we don't really know much about this potential. So what we know is the location of the electroweak minimum. This is given to us by the Higgs wave. And around this minimum, we know the curvature of the potential. This is given to us by the Higgs mass. But what we don't know is the shape of the potential away from this minimum. And this depends crucially on the Higgs-Triana coupling. And as a consequence of this, this means also that the Higgs-Triana coupling determines the nature of the electroweak phase transition. And as also was mentioned earlier, actually these two papers, classical papers, show that you need a deviation of more than something like 30% in the Higgs-Triana coupling from its Tanner prediction to have a strong first-order electroweak phase transition, and this is in turn necessary for the scenario of electroweak baryogenesis. Now, another reason why I think the Higgs-Triangle coupling is quite important is that it can allow us to discriminate between aligned scenarios with or without decoupling. So currently it's looking like aligned scenarios, and by that I mean scenarios in which the Higgs couplings are standard model like at tree level. They seem to be strongly favored by experimental results, which basically show us agreement with the standard model to the current experimental accuracy. And if this is the case, then you can ask why. And one boring option is the so-called alignment through decoupling. That is, BSM states are out of reach, you cannot see them, and then everything looks like the standard model at accessible scales. But another more interesting possibility is that of alignment without decoupling. And is in this latter case, Higgs couplings such as the Higgs trilinear coupling can still exhibit large deviations from standard predictions due to large non-decoupling effects in BSM loops, so radiative corrections involving new states. And if you want to look at such effects, then actually the Higgs-Triangle coupling is a really excellent candidate, because at the moment, as we've seen in earlier talks, the limits on the Higgs-Triangle coupling are still allowed for very large deviations from standard model predictions. So, here I'm quoting one of the latest Atlas results, where you see that you can still have deviations of several 100% from the standard model prediction. But importantly, this will be changed in the future. We know, as we actually heard in just a few minutes ago, the high luminosity LHC will improve quite significantly on this, could reach an accuracy of something like 50%. And then also lepton colliders such as the ILC could have measurements to accuracies of some tens of percent or even 10%. And in the far future, a 100 TeV hadron collider could reach something like 5-7%. So if you're interested in this, please, you can look at the backup or at some of these papers that I'm mentioning here. Okay. So now I mentioned about non-decoupling effects. Let me tell you a bit more about this. So to do so, I will consider a particular model. I will take a CP conserving 2 Higgs doublet model, in which I impose a softly broken Z2 symmetry, under which one of the 2 doublets flips sign. This is to avoid tree-level flavor-changing neutral currents. And then in terms of the 2SU2L doublets, I can write my scale potential as follows, with masses, this off-diagonal mass, which is then softly breaking this Z2 symmetry, and quartic terms. And also I'm defining tan beta as usual as the ratio of the vacuum expectation values of the neutral component of the 2 doublets. In terms of mass eigenstate, I have now 2 CP even Higgses, a CP odd Higgs, and a charge Higgs. And what will be very important for the rest of this talk is that these additional BSM scalars, so capital H, capital A, and H plus minus, they have 2 sources of mass. First is the Higgs VEV through these quartic couplings here, and the second one is the breaking of the Z2 symmetry, which I'm going to parameterize to this Z2 symmetry soft breaking scale capital M, which I relate to this off-diagonal mass term here. So please remember this type of equation. So capital M plus some combination of the quartics times the VEV square. And then the first people to study one-loop corrections to the Higgs-Triangle coupling in the 2 Higgs doublet model were these people here, this paper I'm quoting. And they found up to leading one-loop corrections in the alignment limit the following result for the Higgs-Triangle. So you have a tree-level term plus loop corrections. So the tree level depends on the Higgs mass. And at loop level, you have a first term, which is this top quark loop, basically a standard model-like result. And in addition to this, you now have some BSM effects. And now if you look at these BSM loops, you see 2 things. First, that they have a quartic dependence on the BSM scalar masses. And then that they involve this sort of factor here, which I'm going to call a suppression factor. And actually, this factor depends, its value depends crucially on how the BSM scalar acquire their mass. If they get most of their mass from capital M, the Z2 breaking scale, then this ratio is close to 1 and the whole factor is close to 0, so no BSM effect. But on the other hand, if they get most of their mass from the Higgs VEV, then this ratio is close to 0 and there is no suppression of the BSM correction. In other words, if you take M to 0, you can have large BSM effects at one loop. And you should please note that also this is not actually a problem with respect to perturbativity, because actually the large new corrections at one loop involve a new parameter. Basically these quartic couplings that give you, the BSM scalar mass, which does not appear in the alignment limit at one loop, at 3 loops. So now if you plot this BSM deviation that we obtain as a function of the degenerate mass of the additional scalar for this case where capital M is 0, so this maximum non-decoupling case, you can see that you get potentially huge deviations of several 100% from the Stannmal prediction, and this is without violating unitarity. And these are these so-called non-decoupling effects. And now that I've showed you this at one loop, you can ask, okay, what happens at 2 loops? Can we get new huge corrections? Is something breaking down even if apparently unitarity is not violated? And so to investigate this, we looked at the dominant 2-loop corrections to the Higgs-Reiner coupling in several BSM models. Okay, so let me now turn to the setup of our 2-loop calculation. So what we do is an effective potential calculation, which we have 3 steps. The first one is that we calculate the effective potential to 2-loop order. This gives us an MS bar result. And then from this, we calculate an effective Higgs trilinear coupling by taking a third derivative of this potential with respect to the Higgs field and calculating this at the minimum of the potential. This again gives us an MS bar result. And finally, we convert this from the MS bar to the on-shell scheme, or in other words, we express this in terms of on-shell parameters. So we expand our potential as follows: 3 level plus 1 loop plus 2 loops. And we know that at 2 loop, the diagrams that we need to calculate are 1 particle irreducible vacuum bubble diagrams. And in the BSM models we consider, we want to look at the leading corrections, and these are given by diagrams with additional scalars, like I show here, or additional scalars and top quark. Then let me also mention that we neglect subleading contributions from the light scalars, the gauge bosons and light fermions, because these are much smaller. And we consider scenarios without mixing, such as, for example, for the 2 Higgs-Lavert model, an aligned 2 Higgs-Lavert model. This allows us to evade experimental constraints, and we neglect loop-induced deviations from alignment. So in this example of the 2 Higgs-Lavert model, we have, with respect to the Stannmal case, which I'm showing here in blue, 15 new diagrams, which are in this red box, that contribute to the effective potential. And then we follow these steps that I mentioned on the previous slide. So now let me show you some numerical results that we obtained. And let me define this quantity delta R, which I'm going to use in all the following slides, which I define as the Higgs-Reiner coupling computed in the BSM model minus the prediction in the standard model normalized to the standard model. Okay. So the first thing that we can look at for in the case of the 2 Higgs-Lavert model is this case of maximal non-decoupling effect. So again, we set capital M to 0, and now we plot as a function of the degenerate mass of the additional scalars this deviation delta R, which I defined here on the previous slide too. And so in blue, we see here now the 1 loop result, which is the same as I showed you a few slides earlier. And in red now, what happens when we include our new 2 loop corrections. So on the one hand, we can see that the 2 loop corrections grow faster than the 1 loop corrections, but they remain well smaller in size for this range of masses here. And we verified that unitarity is not violated for this plot. Actually, using the criterion of 3-level perturbative unitarity, we found it is lost around 600 GeV, so outside of this plot. And so typically, for most of this range, we find that the 2 loop corrections, they amount to something like 10–20% of the 1 loop corrections, and at most, they reach something like 30%. Now, another thing that I can consider is what is the maximal size of the BSM deviation that I can get at 1 + 2 loop order, while still fulfilling this criterion of perturbative unitarity. And this is what I'm showing here in the plane of tan beta and m phi, again, the degenerate mass of the additional scalar. So here I show the maximal delta R I can get. And so if you first look at the constant tan beta cut of this plot, for small values of m phi, actually what you're seeing is just exactly the same shape here, like an increase in the BSM deviation. And then you find that the largest BSM deviations are obtained for small values of tan beta and intermediate masses of the additional scalars, something like 600, 800 GeV. This is the case where the BSM scalars acquire all their mass from the Higgs FEV and are quite heavy. If I want to increase their masses more, I cannot keep capital M 0, otherwise I'm breaking unitarity. And so for these points here, we get at one loop deviations of the order of 300% from the standard model prediction, and at two loops an additional 100%. Now, if I increase the value of tan beta, actually the unitarity constraints become more stringent, and then we get smaller effects. And in terms of experimental perspective, we have first a blue region here with deviations of more than 50%, which can be probed at the high luminosity LHC. And then the green shaded area is what could be probed at future lepton colliders, CLIC, or ILC. And for example, the ILC, we know that future 1 TeV high energy stage could reach something like a 10% accuracy, and this is the green area. Now, before finishing this talk, let me also mention that we considered some other BSM models. So in addition to the 2 Higgs doublet model, which I've already mentioned, we also looked at the inert doublet model in a dark matter inspired scenario where the additional CP even Higgs is light in a dark matter candidate, while the CP odd and charged Higgses are heavy. And we also considered a real singlet extension of the standard model. So quite as we expected, actually, we find here that the size of the deviations, both at one loop and two loops, is directly proportional to the number of heavy degrees of freedom that we have. So 4 for the 2 Higgs doublet model, 3 for the inert doublet model, 1 for this real singlet extension. But another thing that we found, which was quite interesting, is that for each of these models, we had a new parameter that only entered the calculation at 2 loop order. So in the case of the aligned variant of the 2 Higgs doublet model, this was tan beta, which does not appear in the 1 loop correction, only at 2 loops. And then you can ask, okay, is it possible to push this to get some larger effects? And here we plot then the red curves are the 2 loop results that we get for the extreme allowed values of tan beta. Tan beta 1, the smallest one, and tan beta 1.4, which is the largest value which we are allowed to have while keeping capital M to 0 and increasing masses up to 500 GeV. And actually, we don't get a large effect. In other words, tan beta is quite severely constrained, and then we only get small effects. On the other hand, in the inert doublet model, we have this coupling lambda 2, which is the quartic coupling of the inert doublet, and this is less constrained actually. We can push it to quite large values. So we can take it between 0, the smallest, and 6, which is the maximum we get, and we see that you can get actually quite large enhancements from lambda 2, but still smaller than the 1 loop corrections. So now to summarize my talk, what I tried to show you here today was the first 2 loop calculation of the Higgs strand coupling in a 2 Higgs doublet model in a scenario with alignment, and I also flashed some results in the inert doublet model and a real singlet extension of the stand model. And the first of my take-home messages is that, okay, 2 loop corrections, for most parameter points, they amount to something like 10–20% of the 1 loop corrections, at most maybe 30%. So on the one hand, this means that the non-decoupling effects that you have at that you found at 1 loop are not drastically changed. But on the other hand, this also means that we will need computations beyond 1 loop, given the expected accuracy of future experiments and their accuracy on the measurement of the Higgs strand coupling. And my second take-home message is that the precise calculation of Higgs couplings, so the Higgs strand coupling, or for example its couplings to gauge bosons, can allow distinguishing aligned scenarios with or without decoupling by accessing non-decoupling effects. And so if you're interested in this, I invite you to also look at these 2 papers, and please also feel free to write to me at this address here. So with this, I thank you very much for your attention.
Okay, thanks a lot for this interesting and motivational talk. Question from the audience? Tanya?
Yeah, can you hear me?
Yes, yes, we can.
Okay. Can you go to slide 11, please?
Yes.
So I'm sorry I'm asking you about something which is not the major part of your talk, but somehow these super large corrections have escaped me so far. So sorry, I have to close the window. It's a bit loud. Sorry. So, I mean, you said you tested against perturbative unitarity. But for example, for any of the models you're discussing, let's say the typical 2x doublet model, do you know what the values which lead to this extremely large corrections correspond to in terms of the original parameters and the potential? So all the lambdas, I mean, what kind of values do they get?
Yes, so I don't have the numbers right here in mind. I can find them. We are talking about relatively large values, meaning that if you are in this case here, you would, for example, not expect to be able to push this model up to very high scales. You might run into Landau balls.
I mean, because what you can do, and I don't know whether you did this or not, but what you can, of course, also do just out of principle is to limit the value of the original potential couplings, right? To say this shouldn't be larger than a certain value, which you can add to requirements of perturbative unitarity, in a sense. I mean, it's testing, and then I would be surprised if you still at one loop, I'm now talking about the one loop results, whether at one loop, if you still get these extremely large corrections. I mean, it can be, I didn't do this calculation. I know if you go to another Higgs 66 one loop and you take all these constraints, you never get these large deviations. So I'm wondering why this happens now in this.
So yeah, I guess it depends on where you cap the values for your Lagrangian quartic couplings. So actually, the criteria that we were applying were those on the Lagrangian quartic couplings.
In addition, so you also have perturbativity constraints in addition to perturbative unitarity, or not?
Yes, but I believe we were not breaking those.
Yeah, this, okay. I mean, this would be, you put your email so nicely on the last slide. I will send you an email.
Yes. Okay, thank you very much.
Yeah, sure.
Okay, more time for questions. Maybe I have a very quick one, and I apologize if we'll sound dumb because, yeah, it's difficult for me to grasp some of this. But we saw early in the session that there are obviously also direct search for like 2HDM particles and so on. And I was wondering if the assumption that you're making in like the soft breaking Z and so on will also impact how potentially the scalars and so on could manifest themselves directly, and how we could look for them in a direct way.
Yes, so for example, the fact that we, for these permutables, for example here, we take this capital M to 0. So this will, for example, not let you push the masses of the scalars very high. So I think for example, for this exact plot here, when the paper came out, I think the limit from experiments was at 350 GeV. So below that was excluded, I think. But so you still have this higher range, which was allowed. And also, of course, if you allow capital M non-zero, then you get slightly more relaxed experimental bounds, I think. I mean, does this answer your question?
Yeah, partly yes, but I think I can follow up on the Mattermost chart. Thanks.
Okay.
Or
okay,
on
thanks
your mail. Thanks a lot. Okay, so I think we reached the last talk of the session. Hua Shen. I apologize if I misspell your name.
Okay, so let me share my screen.
Okay, okay, I think it's. Can you try to cycle the slides?
Yeah.
Okay, now they're in full screen. So please start already.
Okay, thanks. So thanks for this opportunity to have a presentation of the work we have just presented. And we're talking about the calculations of the Higgs production, mainly in the context of the standard model. And thanks for the many great talks we have heard. So I probably will very quickly to several parts of my talks. So introductions, I mean, I think we have heard a lot of, so I will very quickly to go through. So, I mean, important to measure Higgs self-coupling for sure, because we want to understand electroweak symmetry breaking. And also it's relevant for the phase transitions, or if there is phase transitions in early universe. So if, I mean, standard model, we know there's only the crossover, but it's possible that, especially for the electroweak baryogenesis, ask for the strong first order transitions, like the water-like phase transition, or the second order, like ferromagnetic phase transitions in the left part. Also, it will, I mean, decide whether our vacuum is stable or metastable, right? So our standard model predict is around the metastable region and close to stable region within 2 sigma level. So this motivation. So the first target, of course, is easier to measure, is a trilinear coupling, because easier to produce the Higgs for sure. So the question to ask ourselves is how much precision of the trilinear couplings we need for the BSM purposes, right? I just gave 2 examples. There are different angles, of course, to answer these questions. I gave 2 examples. One is from the phase transition point of view. I just using the numbers from the SNOMAS talks given by the Raman Sandra. So the strong first order phase transitions ask for the trilinear couplings relative precision 10 larger than 10%. So I mean, roughly easy to probe. While the general electroweak phase transition, you probably need much smaller than 1% level of the accuracy. And a standard model crossover you need established, probably you need really goes crazy precisions. The second one is, I mean, if at some point we see some deviation, very, very small deviations, okay? So which kind of possible new physics could be rely? And there's one argument by this paper to say that, okay, perturbation theory probably breaks. So you imagine that if you probe the trilinear coupling at the 1% level, you're probably probing the 1 PeV level new physics. So for the Higgs pair production at the hadron colliders, there are, I mean, similar as a single Higgs production, several modes, and the dominant one is gluon-gluon fusion. But the things is the cross section is I mean, there's a strong hierarchy if you're adding one more Higgs, right? So the single Higgs is 10 to 3rd times bigger than the Higgs cross section, and the Higgs is 3 orders magnitude larger than the triple Higgs. And the cross section increase if you could increase your energy, right? If you have more space, of course, you increase. I mean, especially for, I mean, if you have more Higgs, you have you increase more rapidly. So the lambda trilinear couplings, we want to looking at the Higgs cross section measurements with respect to the standard model predictions, right? Or the rely of the Higgs safe couplings. But however, the interpretation of this bond in terms of the BSMs always need additional assumptions on the standard model, right? The common one is that just allowing to change the value of the trilinear coupling. Of course, we already see some. I mean, in previous talks there, you can enlarge these contexts to include the more additional kappa framework or even in the SMAFT. So the current measurements we have heard, and there's, I mean, right now though the measurement, the bond 95% bond is quite weak, but the very, very impressive experiment progress we already see. And there's also future prospects. So here is a table from this paper, you see that from high element HC to the future 100 TeV colliders, and also include E+ E- colliders, include single Higgs and di-Higgs and combinations. Typically, I mean, the high luminous HC current estimate is 50% of accuracy, and this will be sensitive to BSM scenario, usually with the largest new physics effects. And you can also exclude, of course, the lambda equals 0. With some assumptions. So 20% level is the future E+ E- colliders. This helps you to discovered at 5 sigma level of Steinman-like safe trilinear couplings, and an ultra precision machine for these coupling measurement is the FCC future 100 TV colliders. So this will be typically sensitive to the BSM loop corrections. I refer you to the recent studies here. So this means actually, if we want to achieve very precise measurements of trilinear collision, we need a very long time scale of the experiment in the future. So come back to the theory side, the calculations. We want to make the at least the standard model calculation baseline to be as precise as possible, right? So I will quickly overview what the state is right now. So we know that it's the same as the single Higgs. It's a leading order, it's loop induced. So you see that we have seen several times of these kind of diagrams. Next to leading order is photon dependent. It requires a very complicated, especially the double box diagrams. It's just a known recently, a few years, and only is known numerically. And there's actually, we have learned a very interesting lesson from these exact calculations. Before these calculations, what we do is usually we do the 1/mt expansion, okay, something like single Higgs production. And then we scale these with exact MT-dependent Born calculations, right? However, the calculation shows that if you go to the large invalid mass, of course, where these regions we expect that 1/mt expansion is not valid anymore, these reasonable assumptions seems not that great to capture the collective quantum corrections, QCD corrections. Actually, the virtue drives the shapes of the large M invalid mass. Okay, so why this is the case is, I think, is still remaining to be understood. But this is one of the lessons we have learned. So after I have calculated next to leading order with photon mass dependent, there's a pretty major matching scheme to the pattern shower. So also we have seen several calculations to match to the next leading order with pattern showers. There's a interesting aspect we observed is actually for some specific observables like the Higgs pair PT at large PT. This is typically you're looking at Higgs plus 1 jet. Actually, there are some uncertainties is not captured by the normal scale variations in the fixed order calculations. In fact, this is one show that if you're changing the different POHIG and MC10O matching schemes, the difference of the calculations at large PT Higgs is quite significant. Also, if you're changing some of the shower scale uncertainties, you also see some very significant uncertainties that will appear in the large PT Higgs regime. And the remaining next to leading on the scale uncertainty is typically larger than 10%, regardless of the HC or the future 100 TV colliders. So another thing is very interesting by the group up here. They found a large top quark mass scheme dependence. Actually, that is cannot. I mean, it's not independent of the scale uncertainty at some point of view. Okay, and they see that the top quark mass is changing the top mass in the pole mass or in the emissible mass. You find that actually the uncertainty is a similar level as scale uncertainty. Well, if it's very asymmetric, but if you see it's close like plus minus 15%. So something like scale uncertainty level. So it's very surprising result at the beginning, but very important. So there's a lot of analytic information since we still do not understand several aspects of this kind of calculations we have. So there's a lot of progress in the community to try to deepen understanding by carry out the analytic operations instead of the numerical calculations. So this is state of art for if you're looking at the full top quark mass dependence. However, I mean, we can actually, something like a single Higgs production, we can shrink these loops, okay? We integrate these loops as, I mean, this is valid only in the sense that MT is much larger than the invalid mass of the pair, right? So this one, then you get to the tree-level vertex of ground and to the di-Higgs. And this, there's a lot of, I mean, the theory progress in the community to try to calculate this Wilson coefficient to the very high loop, to the 4 loops, actually. And technically, in this case, since it's not loop-induced anymore, easier to achieve very high precisions, okay? So actually, the first neck-to-linear calculations for di-Higgs is, in this approximation, is 20 years, 2 decades ago was achieved. And neck-to-neck leading order was also known in a few years, and there's a few estimations of the threshold logs, different kind of logs, and also some based on this approximation, there one can also try to include some finite top expansion. I mean, finite top effects, right? Based on neck-to-leading order or even neck-to-neck leading order with the 4-top method of neck-to-leading. So this is state of the art. Before our calculations principle, and it's quoted in the yellow report, I think, of the last year. So our aim is push this calculation in this approximation to the n-cube AO. The thing is, I mean, of course, if you see that it seems like a 2-to-2 process. Of course, it's very challenging if you see that it's if you want to perform the n-cube AO, because it's, in principle, there's no such kind of process in the right now we have, okay. But however, for this process is very special. So because we have this hierarchies based on how many effective vertex, the bullet, the black bullet, inserted at a match elements level, okay. So A is of course starting from leading order, contribute to the Higgs. B, the tree level, but it starts to contribute to the neck-to-leading order calculations of the di-Higgs in this approximation, and the C is the square of the is leading order actually contribute to the di-Higgs neck-to-neck leading order. Okay, so we just calculate piece by piece all of them. The lucky C, another lucky C is because for A, they require n-cube AO calculations actually can be cast into the exactly same form as a single Higgs production. Okay, you see that it's single Higgs, but I mean, it's exactly the same as a single Higgs diagrams, right? Except the Higgs is offshore, right? So there's techniques I mean, it's kind of tricks we do, right? We take into account the collect phase space and Wilson coefficients, and then this single Higgs we just ask changing the Higgs mass to be the Higgs pair mass, okay? And this we know, okay? This very profound calculations being done.
You have 2 minutes left.
Ah, okay, yeah, okay. So this will be starting from I-Higgs, okay? And class B, we really need neck-to-neck leading order calculations. We're using QT subtractions, and I will, I think, very quickly to this technical part. So this is, I mean, the virtual part we use in the scat with the summation formulas, okay? And there's different pieces as known in the literature. Then this one is just to calculate Higgs expressed 1 jet, and this is needed to be needed to use the math graph, but you need to calculate the corresponding counter term, all this kind of thing. So this is also new. So the sum of the 2 pieces, virtual pieces, of course, your physical result is independent of which kind of the PT with the artifacture, the cut you post. Okay, so this black ones we checked it, and the C is for fractions. And we have a lot of checks, actually a lot of pieces. Each pieces we have at least 2 independent checks calculations, and some pieces. I mean, this A we have orthogonal checks with next to leading on the GG to Higgs from scratch, and with previous formalism. So the P is never known in the literature, so we need to check piece by piece. And then these results. So I gave the result. The leading order is red, and the next to leading is green, and then next to leading is brown hashed, and the n-cube AO is blue. And you see that, I mean, the significant, I mean, the profound part is is n cube AO with respect to previous order NAO, that is no, it has reduced scale uncertainty by a factor almost 4 if you're looking at the band of the uncertainty band of these. So it's significantly reduced. And right now, the PDF uncertainty in this approximation is larger than scale uncertainty. And we also have C-value. So this gives you that the confidence that we have seen achieved very good predictive convergence in these approximations. So this one can also rely the the lambda HHCF coupling, and to see that whether the shape changes with the QCD corrections, and we don't see. Actually we don't see the shape changes. When looking at the Higgs pair invalid mass distributions, the scale uncertainty is significantly reduced as well, and the shape is very stable with respect to the previous order. So of course we need to include the final top mass because M Higgs is of course much larger. It's larger than top mass. Actually, it's only most of the events is close to the 2MT or even above 2MT. So we need to include the 4 top mass and the top mass final top mass corrections. So we have the NKAO, that K is up to 3 infinite top mass calculations, and NAO up to 1 for the 4 top mass dependence. And there are several different approximations. There's no unique way how to do this, of course. So there are several approximations we have tried. We just, for example, for here it's very most exclude one is we just have the 4 negative leading order of the 4 top mass dependent and add the collections in the infinite top mass limit. Or another way we think is best in our 3 approaches is just using the K factors. Of course, different approaches, we have different assumptions behind. So this is, we think is the best we have achieved. We just imposing the K factors to the 4 NAO top mass dependent result. So here is the result. So one thing I want to mention is the 4 top NAO corrections. We have actually also used the existing code in the Higgs box framework. So here is actually we think is the best prediction we provided. So same thing, n cube AO enhanced NAO by 3%, but the scale uncertainty is reduced also to 3% level, below 3% actually. The missing top quark mass uncertainty, you have different way to estimate. One way of estimate, we can try to have the difference using the difference of different schemes of incorporating the final top mass corrections. So this we estimate around 5%. The top quark mass scheme uncertainty, of course, is unknown yet. So this we do not expect it to be improved if we already taking the MT to be infinity in the n-cube AO calculations. So here is the invalid mass distributions, neck-to-neck leading order versus n-cube AO, and compare with the 3 different top mass approximations we have tried. The message here is, the scale is significantly reduced, and the top mass is effect, final top mass effect is very crucial. Even you just, ignore the top mass in the correction itself, then it may give the very wrong result at large invalid mass, which the final top mass is crucial, right? So the red, this is what the red cube is sure. So let me draw my conclusions. So we have carried out n-cube AO calculations for Higgs pair production of the ground-ground fusion with the infinite top mass limit. The scale uncertainty is significantly reduced to be below 3% or 2% at the HC energies or future collider FCC HH energies. PDF uncertainty is a bit bigger than this kind of scale uncertainty at the moment. The predictive convergence in the process shows pretty good at n-cube AO. However, there are still some remaining theory challenges we need to tackle in future. The one thing is remarkable one I have emphasized already is how to improve the bigger top quark mass scheme dependence already seen as negative leading order, and how to further improve the final top quark mass correction. There are some, I think there's some progress in the literature, and also how to estimate or account for other theoretical corrections, or estimate other theoretical uncertainty like the electroweak corrections or the finite the MB corrections in the loops, or some parametric errors from different sources. So thank you for your attention. Okay.
Thanks a lot for the very comprehensive talk. So we do have a hard cut at 1:30 for the poster session, but that means that we can accommodate a few questions. So anybody wants to start commenting on this interesting new outcome of the prediction?
Excuse me, I have a naive question for the last point you mentioned as remaining challenges. So about the top quark mass scheme, is there some way to find which one is at least better with respect to the experimental data for this point?
So you mean that if there is a experimental data existing? Of course, yes. I mean, as precise as this one, yes. I mean, if you can measure the Higgs cross section at the 10%, 15% level, 10% level, let's say, okay, then yeah, data may tell you which scheme is better, right? Without further improvement on the theory side, yes.
So you mean the cross section of the di-Higgs cross section?
Yeah, if you have the same level of the.
Is there other observable which are already available from the current luminosity? Is there some observable we can judge which method is better from the existing observables? Is it possible?
I mean, my short answer is I don't know, but I think one can also try to look at with this kind of top quark mass scheme dependent on the single Higgs in other observables. Yes, but how can you draw that one top mass is favored in one process can be drawn to this double Higgs different process, completely different observable. So what kind of conclusion you can draw? I personally I don't know. Right?
Okay,
so,
thanks.
Okay, thanks. Chance for the last question on the parallel session at ICHEP 2020 for the Higgs. Okay, Singu. So I apologize if I misspelled your name. Please start.
Okay, so for the, can you also do this calculation for the di-Higgs PT, or is more complicated?
Yeah, so we have yeah, we can have the information. So I assure you that actually, except the invariant mass of Higgs, since the A part, the single Higgs-like part, we do not have Fourier differential calculation at n-cube AO level, right? So we have to do some approximations to estimate for other observables. So this example, the delta Y liquidity, you can apply to these two same of the PT Higgs pair as well. Using, for A part, we just using the global. Well, A actually decomposes into two parts as well in order to guarantee the scale cancellations with the A and B. There's some subtle scale cancellations between the two ports. But you see that in principle, we need to do some approximations for n-cube AO for other observables. And in these approximations, yes, we can provide other differential observables, yes, for sure. But how these kind of approximations can really be the final n-cube AO, this we haven't estimated. So for some observable, I would say that, for example, the rapidity distribution, I would say that it's more or less okay because we have already have n-cube AO of the rapidity distributions, and we see that the K factor fairly flat. So this approximation use is justified. But for PT Higgs 6, I think it's probably not that clear. Okay, so right now, yeah. So right now we needed to do some approximations for other observables at the incubate level.
Okay, thanks.
Okay, the very last question. Anybody wants to take it? Okay, if not, we can thank the speakers for this session again. Remind you that you can still reach them through Mattermost and the various channels that have been advertised. And in 6 minutes, we will start the last poster section where we, of course, you will all be welcome to join the discussion and ask more direct questions to the speakers. If not, thanks a lot, everybody, and see you probably in the parallel sessions, in the plenary session next week. Bye.